In this video, we will go step by step through a complete hardware design in KiCad 7 for a Bluetooth-capable STM32 microcontroller. From project creation through to drawing the schematic and figuring out the circuitry required, laying out and routing the PCB, and finally ordering the boards at PCBWay. The board you are seeing here is something very similar to what we are going to create and features an STM32 WB55 microcontroller, USB Type-C connector for power and data, as well as a Tag Connect programming header and a chip antenna. Most of the design we will be creating in this video, given the time constraints, will be nearly identical. However, we will be using a generic UFL antenna connector instead of a chip antenna and won't route out all of the microcontroller's interfaces. I will put relevant links in the description box below, as well as timestamps of all sections of this video. I really hope this video helps you design your own STM32 Bluetooth-capable projects, and if it does, please do leave a like, a comment, and subscribe for more hardware design content in the future. A huge thank you to PCBWay for sponsoring this video. The PCBs you saw at the beginning of this video were manufactured and assembled by PCBWay. Those were 4-layer boards and they included double-sided assembly, and they did a fantastic job. I'll show you at the end of this video, once we finish the design of our own STM32 Bluetooth-capable hardware, what the ordering process is like at PCBWay, what files we need to submit, and what the usual durations and costs are. So make sure to check out that section near the end of the video. Make sure to go to PCBWay.com to check out their services, but also make sure to follow them on Instagram to check out a selection of designs that PCBWay have manufactured and assembled. We can only scratch the surface in one of these fairly short YouTube videos going through the whole design, but I do have full-length courses available via Fedivel, and I'll leave a link to this in the description below. Signing up to courses really supports me, helps the channel, and allows me to make this free content. I have a mixed signal hardware design course with KiCad, using KiCad 6, but it's applicable to many different ECAD tools, as well as an advanced digital hardware design course, where you can learn how to design with BGA packages, high-speed systems such as DDR3 memory, FPGA, system on chips, and so on. Again, I'll leave a link to this in the description below, and thank you so much for your support. We're now ready to move over to PCB design. Before that, just a quick few words. For example, this symbol hid from us if we go to Cube IDE, these 80-0 and 81 pins, and these are unused in our case, so they also don't appear on the symbol here. With that being said, let's move over to the PCB design. The way we can do that is go to the top toolbar and click on Open PCB in Board Editor. That will launch the PCB editor. So we want to create a new file, so click Yes, and we are greeted with a blank PCB editor, and this is where we'll be doing the layout and routing, and we have this new set of commands and controls and toolbars that is different to the schematic editor. Before we start any PCB design, we have to set up our tool, so that could be net colors, it could be setting up design rules, setting up the layers, how many layers on the PCB we have, and so on. The way we do that in KiCad is in the top left, the second button on the toolbar, Edit Board Setup. We click on that. We have many different options that we should adjust before we even start placing components on our PCB. The first section here tells us about the layers that are available. So for example, we have a paste layer. This is where the solder paste will be printed on. The Silkscreen, which is the typically white ink you will have on your PCB, for example, for text and so on. Mask layer, which is the solder mask, front copper, back copper, and many other different layers. Most of them should be enabled, but I will turn off the fabrication, adhesive layers, as well as these user eco layers, because we won't be using them in this design. Then, if we go to the second tab here, this physical stack up, we could of course try and route this on a 2-layer PCB, but these days 4-layer PCBs are very, very inexpensive as well, and unless you have a good reason to go to 2 layers, it's oftentimes more advantageous and easier, quicker to do it on 4 layers, and also has better physical properties than a 2-layer board in many of these digital cases. So we'll go with 4 layers for this one. So when we add in the 4 layers, we can see we get this new stack up here. So we have 4 copper layers, front copper, inner 1 copper, inner 2, and back copper. In between we have dielectric materials, top and bottom we have solder masks, paste layers, and silkscreen layers. What we'll need for this design is an impedance controlled board because we're routing RF traces. So we'll click on impedance controlled. Now, in reality, for this particular tool, it doesn't matter too much if you click this or not, but what we should adjust are the thicknesses of our individual layers and the types of these layers, as well as the dielectric constants, and this is something you would then communicate with your fabricator as well. Where we get this information from is from your PCB manufacturer of choice. In my case, I went with PCBWay, and any manufacturer will have this. They will have a, for example, capabilities section, but they will also have, for example, layer build-up or layer stack-up section. So that's what I've opened up here. And these are stack-ups. If we scroll down, for example, for 4 layers, or for 6 layers and more, these are standard stack-ups that they are okay with producing, that they find easily producible, and will be the most cost-effective. A typical 4-layer PCB is 1.6 millimeters thick nominally, and PCBWay has 1 ounce outer and 1 ounce inner copper foils. And this is where we read off the stack up. So layer 1, which will be our front or top copper layer, will be copper 18 micrometers plated to 35. Then we have a pre-preg material of a certain thickness, so 0.11 millimeters. We have this 2116 dielectric with a certain constant. Then we have the first inner copper layer or inner copper foil. And then we have this core with a certain thickness and so on. So this information, layers 1 to 4, as well as the pre-pregs and core materials, we move over to KiCad. So for example, for the dielectric 1, I would click on the 3 dots. I'll type in 2116, that was the dielectric, and our epsilon R, which is our dielectric constant, was 4.29. Same thing for dielectric 3, and the core was the center material. This is FR4, and that was 1.2 millimeters, and typically that has a dielectric constant of about 4.6. The copper thicknesses are okay, so that's 35 microns on each layer. And then we have the masks. We can choose a specific material. It's not really too important in this case. The pre-preg thickness was, of course, 0.11, and now we get a final board thickness of about 1.6, so just under 1.6 millimeters. Of course, this is not taking into account any tolerances. It's always good to import what your board stack-up is into your PCB design tool. And this is something you should later then also communicate with your manufacturer, and we'll see how to do that when we come to the board ordering process. Next tab, we could select, for example, the copper finish, or you might go with hot air surface leveling lead-free. We can change solder mask expansions, solder mask minimum WEPs, and so on. In KiCad, they leave the solder mask expansion to be 0 millimeters. You can leave this as 0 millimeters and let the fabricator adjust the solder masks, but typically I would set it myself. Typical solder mask expansion values might be 2 to 3 mil, and that's in imperial units, and 3 mil is about 0.08 millimeters. So we might type in 0.08 millimeters here. Solder mask minimum web width we can find by going to the PCB manufacturer. So looking for PCBWay and then looking at the solder mask and scrolling down, this depends on the color of solder mask you choose. So if we choose, for example, red, black, blue, or white, this might have a different solder mask, might have different solder mask parameters than if we go with green, for example. And on the PCBWay website, that's what we see as well. So for green, the solder mask has certain parameters, for example, a minimum bridge of 100 micrometers. But for other colors, such as red, blue, white, and black, this bridge increases. So you need to know this ahead of time. We'll just go with green. So that's why we can go with a bridge of about 100 micrometers, but they do recommend 125 micrometers or microns instead. So I'll type in 0.125, then go into text and graphics, and we'll just leave this as default for now. Formatting, text variables, we can all leave as they are. What's the most important is setting up your design rules, however, and in particular these constraints, predefined sizes, and we'll set up the net classes as well. Constraints and design rules are what rules we have to adhere to make sure that our PCB is manufacturable. So for example, if we're routing 2 traces, these traces can't be too close to each other, otherwise we can't etch the gap in between those traces. Also, the traces can't be too narrow themselves, they have to have a certain width and so on. For example, drill holes can also not be too small or too large, and this is the information we fill in on this section in the board setup. Capabilities depend on your manufacturer of choice. For this, of course, I'm going with PCBWay, and they have their own capabilities section. So going to the PCB website /capabilities, we can find the capabilities here. And this information we need to transfer over to our ECAD tool. So for example, they can do minimum drill sizes 0.2 up to 6.3 millimeters, the widths of annular rings, the hole size tolerances, and so on are all listed here. That being said, these are the minimum possible manufacturing capabilities, and you should aim to stay away from them. There's no talk about what these things cost on this page if you go below these minima. To see how this all affects price, let's go over to the actual online quoting system, and this is quite interesting to play with. So for example, for 100 by 100 millimeter PCB, let's go with 10 PCBs, selecting 4 layers and leaving everything else as default, the base cost is about $51-ish for 10 PCBs. Now this is assuming a minimum track size and a minimum track spacing or feature spacing of 6 mil. 6 mil is about 0.15 millimeters. So if we go down to 5 mil, so that's about 0.13 millimeters, the price hasn't changed. But if we go down to 4 mil, so that's about 0.1 millimeters, we see the price has increased. So without a cost adder, we can go down to 5 mil traces, and again 5 mil is about 0.13 millimeters. Same for the hole size, so automatically it's selected 0.3 millimeters, 0.25 millimeters doesn't add a cost, but if we go down to 0.2 millimeters, we can see the cost jumps dramatically. So therefore we want to keep our hole sizes to 0.25 millimeters, or preferably to 0.3 millimeters or above. Solder mask, choice of solder mask color also impacts the price. So if we go to green to matte black, we see the price jumps up. So for prototype, we might as well just go with green. Silkscreen also affects price in any of these other options. So for example, the surface finish will affect price as well, and so on. All that being said, is that we need to take these capabilities with a slight grain of salt. We want to stay above these capabilities, and also that they don't add cost unnecessarily if we don't need these capabilities. So going back to KiCad, our minimum clearance, let's stay away from the minimum. We saw that was about 6 mil, 5 mil, so let's go with 0.15 millimeters, and same for the track width. This will not add any cost and is perfectly okay for a 4-layer board. Minimum connection width is the minimum feature size, so if we're doing a copper pore, for example, or polygon, that would be 0.15 as well. Minimum annular width and minimum via diameter is the next section. When it comes to annular ring, this is to do with plated drill holes and vias, for example. Typically we have a via where we have a drill and we have a finished hole diameter. So we can see the image on the top here. The finished hole is after plating. So after it's been drilled and then plated, we get the finished hole diameter, which is what we typically specify in our PCB design tool. Then the diameter of the pad we have as well, and effect the difference between the diameter of the pad minus the diameter of the finished hole divided by 2 is the annular ring. So OAR, outer annular ring in this example. We of course have the same thing for inner layers as well. The calculation, typically the finished hole is 0.1 millimeters smaller than the drill hole. And this is what we see here. So we're actually using a drill hole that's 0.1 millimeters larger than the actual drill diameter we want. So if you want a 0.3 millimeter hole, we drill 0.4 millimeters and we plate down to 0.3 millimeters. Therefore, our annular ring calculation is actually like so. It's pad minus drill plus 0.1 millimeters, all divided by 2. And this gives us the annular ring. Typically, an annular ring of 0.15 millimeters won't be a cost adder. Minimum via diameter, I'll go with 0.65, and we'll see why in just a second. Copper to hole clearance, we typically want 0.25 or larger. So we'll go with 0.26 just for this case. And copper to edge clearance, we'll go with 0.3 millimeters, as that's a sensible copper to edge clearance. Again, this is taken from experience and taken from PCB capabilities from your chosen manufacturer. Minimum through-hole diameter, we saw that 0.25 millimeters does not add cost, so we'll go with that. Hole-to-hole clearance will go a bit larger at 0.26. So now we filled in all of our constraints, at least the ones that KiCad allows, and then we go to predefined sizes. In KiCad, we have to define our track widths, vias, and differential pair sizes before we can begin routing. In terms of tracks, we might go with a 0.15 millimeter track as our smallest, and we might have traces that go, for example, 0.2, 0.3, 0.5 and 1 millimeter. This is just a selection, just a basic to start off with, and these are the track widths we can then choose and route out when we come to PCB routing. With vias, typically I will go with a 0.7 millimeter diameter via and a 0.3 millimeter hole. Doing our calculation, so 0.7 minus 0.3 plus 0.1, all divided by 2, gives us a minimum annular ring of 0.15, so within spec, and that's why I choose these via properties. It could be that we might need a smaller via hole, so 0.25 millimeters. Remember, this was the smallest we can do without a cost adder. And that allows us to reduce the pad down to 0.65 and still have our minimum annular ring of 0.15. And finally, we'll just add a larger via, just in case, at 0.4 millimeter finished hole and 0.9 millimeter diameter. What we haven't talked about yet is impedance control. I won't be going into detail on what impedance control traces are in this video, but we do need to use them in this video. I please refer you to my video number 3 on my channel, which goes over what impedance control traces are, when you need them, and how to set them up in KiCad. Effectively, impedance control traces are needed for high-speed signals, RF and digital, that we match impedances to drivers and receivers. We'll need this for the USB differential pairs, as well as for RF sections. We'll need to use impedance control traces, and this depends on the stack-up. And remember, the stack-up was what we set up earlier in our KiCad tool. To get the trace widths we need for the RF sections and for the differential pairs, we need to use an impedance tool or impedance calculator. And there's many different variants out there. Best thing is to talk to your manufacturer. So I would send PCBWay a message, for example, and saying I need a 50 ohm track with this particular stack up. What trace width do I need? This is definitely something you should do, but you can also get a ballpark figure by going with the impedance calculation tool. In this case, this is from PCBWay. We will be using outer layer traces in this example, so we're using surface microstrip. There are also other different forms of impedance control traces. What we need are 50 ohm traces for the RF lines, and we need to figure out what width we need given our board stack up. So remember, we're routing on an outer layer or bottom layer. We have a prepreg that's 0.11 millimeters and a dielectric constant of 4.29. So I'll type that in, 4.29 dielectric constant. Thickness of the copper was 35 microns. And the height, so the height or the thickness of the dielectric was 0.11 millimeters. Therefore, if we just try out some trace widths, for example 0.2, we can see that already gets us pretty close to our target impedance of 50 ohms. So to get the impedance higher, we need to reduce our trace width. So let's try 0.18. 0.18, and that overshoots a bit, so maybe something in the middle, 0.19, and there we go. We hit 50 ohms directly. So we need a 0.19 millimeter trace width to give us a 50 ohm controlled impedance trace for this particular stack up. Again, talk to your manufacturer. It's the best and easiest way to do it and most accurate. So in KiCad, let's add a 0.19 millimeter single-ended trace on the left-hand side, but we also do need to set up differential pairs. And for differential pairs, we have, again, this USB differential pair should have a 90 ohm differential characteristic impedance. For this, we will use the edge-coupled surface microstrip model, so one below the surface microstrip, and we have the same board parameters as before, copper thickness of 35 microns, we have a dielectric thickness of 0.11, and an epsilon r of 4.29, our dielectric constant. Now we have two parameters to play with this differential pair. We have the trace width itself of the individual positive and negative parts of the differential pair, but we also have the trace spacing, so how far apart they are or how close. Typically, for USB, we would also want a 50 ohm single-ended impedance, so we'll use the same trace width as we had with a surface microstrip to start with, 0.19 millimeters. And then we can see the single-ended impedance, so Z0, is about 50 ohms, which is what we pretty much had before in the single-ended case. However, we still have the spacing to play with, so this S parameter, and that will influence, to a certain extent, the differential pair impedance, which at a spacing of 0.15 millimeters gives us a differential pair impedance of 100 ohms, which is just over 10% higher than what we want it to be. So if we reduce the spacing, so for example to 0.12, we actually bring down the differential impedance. The problem is, we've now reduced our spacing down below the minimum clearance we had, which was 0.15 millimeters. So the lowest we want to go with the spacing is 0.15 millimeters. However, that means we don't hit our differential pair impedance target, which means we need to adjust the trace width. So if we change that to 0.22, we can see that, of course, the single-ended impedance drops because we've increased the trace width, but our differential pair impedance now gets closer to 90 ohms. Now keep in mind, we are using USB 2.0 full speed, which is these days a very, very slow interface, and we are probably going to create a very small board, so we don't actually need to control impedance, but it's a worthwhile exercise doing to get an approximate value for impedance. So let's say we go with a 0.22 millimeter trace and a 0.15 millimeter trace spacing. So moving that over to KiCad, we add a differential pair with a plus at the bottom. So trace width was 0.2 and a 0.15 millimeter gap. And then we also have the via gap. So when we place differential vias, we don't want them spaced a certain amount, and we'll just space them 0.5 millimeters to start with. Let's see if we even need vias. Now we have all of our tracks predefined. We have our base tracks as well as the controlled impedance traces. We have the vias and a set of differential pairs for USB 90 ohms. Then we have net classes, and these net classes are actually taken over from the schematic. Remember, we set up the net classes with these patterns, but we haven't imported anything from the schematic yet, so we don't have any nets matching. We can also add in custom rules if we want, and violation severities just like we had with the ERC. But for now, we can press OK and press save, and now we've set up the basics of our board. On the right-hand side, we can now see that we have less layers than what we started with. We only have front copper, inner copper, the top, inner copper bottom, bottom copper, the paste, silkscreen masks, and some other layers. So now we're ready to import the components onto our PCB. Now that we have our PCB set up and our PCB design rules set up, we have just the layers we need on the right-hand side in the appearance panel. As we saw earlier, we can also go through other tabs looking, for example, at objects, We can change their visibility, what we can see, what we can't, and also go to nets, where we already see we have our net classes imported. To now have the components imported, what we need to do is either press F8 or go to this top right toolbar, update PCB with changes made to schematic. We click that button. We will get this dialog box, and this tells us what will happen to the PCB. So we're going to add all our symbols that we have on the schematic, use those footprints to add them to the PCB. We hope that there are no errors and no warnings, and then we can click update PCB, close, and then without clicking, I can move my mouse. I can zoom in, zoom out with my middle mouse key as usual, and I'll just place this set of components by left clicking, and then I can click away. Middle mouse button drag, I can move around the PCB. And now I have all of the components that we created on our schematic as symbols, and then we linked with footprints on our basic PCB. To view this in 3D, I can either go to the top left, View, 3D Viewer, or I can press Alt-3 on my keyboard, and this will then display a 3D view. I can click with my left mouse button and drag to then rotate this PCB in 3D view, again middle mouse wheel to zoom in and zoom out. And you can see KiCad has now defaulted to a default board outline. And you can see board outline is missing or malformed in the top left because we haven't defined our board outline yet, and that's something we'll get to later on as well. But here we can see all of the components, USB connector, our STM32 microcontroller, various passives and so on, but we can immediately see a couple of problems. And this is something that bugs me with KiCad quite a bit, is that the library links are very often messed up. For example, the connector, this Molex Pico blade, which we can see here with these 4 3-holes, or X2, which was our high-speed external crystal, or X1, which was our low-speed external crystal, they're missing 3D models, although they should be included with the KiCad libraries. So we have to fix those links. First of all, I always think it's very important to have all 3D models in place. Of course, for the tag connect header, or the pins rather, we can see we don't have a 3D model because they're just pads and through holes. So let's go and fix the 3D models first of all. We can close this 3D viewer, top right. For example, clicking on our Molex Pico blade, or double clicking rather, this will open up this footprint properties panel, and we can see our various tabs, which we might explore later as well. But for example, the third tab, 3D model, we can see that it's linking to, for some reason, KiCad 6, which I don't have installed on my computer, or maybe I deleted it, so maybe that's the issue. But you can see I have an X, a file not found. So if I click the little folder icon next to it, it jumps to where it's trying to find the models. So under Program Files, KiCad 7, and so on, 3D models. And these are the KiCad default 3D installed models. So we're looking for 530480410. For some reason in KiCad 7, maybe this doesn't exist anymore, but it still exists in the symbol and footprint libraries. So this I always find very frustrating. So the way I would then find the missing 3D models, if they're not in the KiCad libraries, I would simply type in the part name. For example, for this Molex Pico blade, it was this number. Go to the Molex website, which happens to be the third result. Scroll down, and we can find the 3D model as a step file, which is zipped in this case. So I'll download that. Then you have this zip archive with the step file in it. So now either you can put that in the path that, for example, KiCad effectively sent us to, so this .3D shapes folder, and then copy this name, change that to step. So that's one option, but for the sake of simplicity, I'm just going to copy it into the project so we can make a new folder with step files, for example, so we have it locally, or you can do it globally, however you want to. For the sake of simplicity, I'm just going to copy it in here into my local project folder, then back in KiCad under footprint properties, I'm going to click this folder icon again on the right and navigate to where I saved it, and then select my step file, double click, and you can see it's not centered properly, so I can play with the offset controls, rotation controls, and so on to try and get this aligned. Now, this is unfortunately very manual. I might be wrong, but I don't think there's another way of actually aligning this. For example, I could align in other programs the axes from the pin to the through hole and so on, but it looks like we have to do this manually. So now I've roughly aligned this 3D model with the footprint with the through holes using the offsets, and I can click OK. So again, pressing Alt-3 to get the 3D viewer. Now we can see we have the connector model in place as a 3D model as well. So I'm going to do that, the same procedure for X1 and X2, my crystal oscillators, just to make sure we have all the 3D models in place, and I think that's very important. For example, when you would hand a design off to your mechanical team to check positionings, clearances, and so on. So I'll do that in my own time, but please make sure to do that on your end, depending on what schematic you've designed. Please add in the missing 3D models. If you can't find the 3D models via the manufacturer website, which is quite often the case, I can highly recommend two websites. First is 3D Content Central, and I've managed to find many fairly accurate step models for the parts I'm looking for here, as well as GrabCAD. So those two websites, if you can't find them on the manufacturer websites as before, please go check out those sites. And using exactly those methodologies, we can see we now have all of the required 3D models in place. So for X2, J2, as well as X1, which had the 3D models missing. And now we can finally get around to starting with the layout of this PCB. But these are the essential steps that I would do first. Make sure my footprints and models are all there right from the get-go. Before we get started with layout, on the right-hand side, remember we did add net classes before, and this will help us visually identify where certain nets are and where connections need to be made. You might have already noticed these rather thin air wires, which sometimes are crossing over, going vertically, horizontally, many different angles, and these are what's known as part of a rat's nest. And these are the connections that need to be made and haven't been made yet. And this is again taken from the schematic. So for example, USB D- has this air wire going to the top right because we have to go to our ESD protection. And our ESD protection has these air wires, parts of the rat's nest, that need to go to the USB Type-C connector. And this, of course, we have to keep in mind for routing later on, but of course also for layout. We wouldn't, for example, want to place our USB connector completely different to where our ESD protection is, so the air wires, these rat's nests, can guide us. The reason why I'm bringing that up first is because this is very important for layout, but also coming back to net classes on the right-hand side, the reason we defined those is then also to make our life easier, because we can assign these net classes different colors. So for example, on the right-hand side on the net classes, if I go, for example, to serial wire debug, you can see this little checker mark on the left-hand side. If I double click on that, I can define a color for that net class. Now I could have done this in the schematic as well. In the PCB, we can use this color select tool to then, for example, assign a color. Let's say I'm just going to go with blue, press OK. Then on the net display options below, I'm going to change my net colors from rat's nest to all colors. With that option enabled, we can now see that all the serial wire debug nets, for example, for this tag connect header, so data IO, clock, trace, and the reset line are all in the color we just selected, as well as the rat's nest. So these air wires are also the same color, but of course also the nets that originate or end on the microcontroller are colored in blue, whereas all the other nets are still in other colors. And this is an incredibly useful tool when doing PCB layout and routing to quickly visualize where connections need to go. So for example, we now see this tag connect header probably needs to be aligned somewhat vertically above this microcontroller, or depending on how we rotate it later on. Same thing if we change, for example, the RF nets on the right-hand side, double click on the checker mark, and we might change this, let's say, to yellow. All the nets that are yellow are RF nets. And typically I give these more critical nets, such as RF for high speed, brighter colors to really jump out and say, okay, these are critical nets, they need more spacing, they need to be routed a certain way, and so on. So other than the design rules you can set up, I find colors to be a very, very important tool. And we can set that for everything else we have in this design. So USB, we could, for example, give this a color green. Power, typically we might want to give this a red, and of course you could distinguish between different types of power. If you have, for example, a 1.8 volt rail, a 3.3 volt, and so on, you can give these nets different colors. Ground is also a very important one to change on its own. And ground, because it starts with G, we could say it's maybe a gray or a green. I will typically always give my grounds a somewhat grayish color. So I'm a tiny bit colorblind, so I'm not entirely sure if this is gray or more green, but let's say it's gray, and this immediately identifies to me where ground is. I can see, okay, here's ground. Or this pad is ground, that pad is ground, and so on, just by colors rather than having to read nets. So immediately I've gained valuable information just by designating net colors. We can do this for any other signal we want. For example, the switch mode power supply, we don't have a net class, and that might be a good thing to do as well. If you want to retroactively do that, we can go back to the schematic. So as we've named our net somewhat sensibly with the same starting characters, we can then go to the top left, edit schematic setup again. And this is where we edited our net classes previously. So you want to add a new net class, press plus at the top, and then we'll call this SMPS or switch mode power supply. And then we also need to assign the net class at the bottom. So the plus at the bottom, / for local, SMPS star, and that now selects all of our SMPS nets. We just assign this to a net class, and we'll assign this to SMPS. Press OK, save the schematic, go back to the PCB, top right. And now on the right-hand side in net classes, we can see as SMPS net has been added. So we can double click on the color. And let's change this, for example, I don't know, to some pink, for example, something that's different. And here we go. We immediately see where the switch mode power supply nets are. So 33, 31 on this new color. we can see that the junction between the inductors is the same and that output is a different color, and the output capacitor C14 also now has a new color. And I find this an incredibly intuitive visual way of identifying where relevant nets are and where groupings of nets are. You can of course change the visibility, so it's just for the rat's nest, those colors, which I find a bit hard to see, and that's why I typically always leave it on all. And we can of course hide the rat's nest or show it. And I prefer to show it for the most case. You can of course hide rat's nests for specific net classes and so on, but for now we'll just leave everything on. So I'd recommend you do that for your own designs and split them up into logical colors, at least to you logical, but for me I really like to keep power in the kind of reds, ground either grey or green. I prefer grey. In any case, now we've hopefully got a bit of a better visualization of what's going on and what parts on the PCB need to be connected to what other parts on the PCB. Before we even start with routing, we need to have our layout sorted, and then we define our board outline, maybe add some mounting holes and so on, but we don't really touch routing unless we've done at least some sort of rough layout. Occasionally, as we'll see, we might route out certain bits of track, for example, to see if we can get past some components, but for now, we just want to use these colors and these rat's nests to guide our decision of where to place components. Given that this is a fairly simple board, this might not take very long. This is an iterative process, so I'll place one component, place another, I'll see that there's constraints because one might not fit, and I'll have to move things around. So your first solution might not be the optimal, and might not be the solution you go with. Always keep that in mind. In any case, for this design, we somehow or somewhat have a centerpiece, and that's U2, our microcontroller. So we'll start with this as our foundation, maybe let's say our origin, and we'll build around that. So by clicking on it, I can select the part, I can then press M to move. I can press cancel to reset it back to its original position, because initially, for initial layout, I want to change my grid. The grid we can see at the top, I can press this drop down and we can see I have many different ones available. We have these imperial grids, so in inches or thousands of inches, and we have this millimeter grid. I typically will use millimeters, and of course if you're in the US or some other country that uses imperial, then you would go with imperial, but I would suggest going with millimeters and using a fairly coarse grid, and coarse in this case meaning maybe 1 millimeter or half a millimeter, to start doing your layout. So I can select the grid of 1 millimeter, and it's always important that you align all components to a grid. I wouldn't suggest going with grids, for example, as small as, for example, 0.01 or something like that, even when you're fine-tuning the layout. So the smallest grid I might go with is 0.1 millimeters. But to start with, we'll go with a 1 millimeter grid, click on U2, press M to move, and we'll just move that in its own little section. For example, like here, and you can see if we double click on this component, I've moved it to position that is currently on the grid, and we can change the origins and so on. But I just like to start off with somewhat sane, let's call them numbers, so round numbers, 70, 70, somehow that is fine. Then we build around this part. What I'd suggest you do, and I typically work with 2 monitors, but for the sake of recording, this is all on 1 monitor, you should have your schematic next to your PCB layout tool. So for example, I know this is a tiny bit cramped, this is just to show you, on the left-hand side, on the right-hand side, wherever, you would have your schematic, on the other side, you would have your PCB, and anytime I click on a component on the schematic, so for example C10, the PCB editor in KiCad jumps automatically. And this is really useful if I'm routing out sections. So if I want to, for example, connect my microcontroller to the UART connector, I would just click on the connector and I can then move that over to where it needs to be. The same thing works the other way around. So if I'm on the PCB editor and if I click on J1, the schematic will jump to J1. This is a very useful tool, and it always pays off to also have the schematic open while you're doing PCB layout and also PCB routing later on, just to make sure, because we've designed our schematic to have hopefully somewhat of a logical flow, that we go, for example, from J1 arc to connector, through to the ESD protection, through to the microcontroller. So typically your PCB layout might also follow that logic. Of course, depends on space constraints and so on. Also, with any PCB design, there are sections that are more critical and less critical than others. And it's important to identify those early on and already place those more critical sections, for example, first, or route them out first. And so let's try and do that here. What's, of course, most critical will probably be this RF section. This is sensitive circuitry. We have digital circuitry very, very close by on this board. So it's important that we, for example, prioritize the matching network, the filter and antenna connections, and aim to keep those short and close to the microcontroller. Similarly, for switch mode power supplies, you want to keep loops short, nodes short and compact. For example, especially these switching nodes, for example, these LX nodes, they need to be nice and compact, close to the microcontroller as well. Very similarly, the high-speed external crystals and the low-speed external crystals, these are sensitive analog traces, short connections away from aggressors, for example, higher speed switching circuitry and so on. The USB traces, for example, the USB differential pair, although it's only full speed, we want to route that with K as well. Then also the serial wire debug might be less critical, but then of course there are even less critical parts. For example, the boot 0. That's basically just a DC signal and we hook that up to a switch, so maybe we can prioritize that to be last. Similarly for the NRST line, which goes to the tag connect header, that isn't particularly critical either. Of course it has to be connected, but how we route it isn't that important. Same thing with these TX and RX lines. Yes, they could have fast edge rates, but compared to, for example, the RF sections, the UART is less critical. What is also critical is the placement of the bypass and decoupling capacitors. These need to be close to the relevant power pins on the device. So this is something you might want to prioritize as well. And so PCB design and hardware design is basically a list of compromises. We have to see what sections influence the other, what do we need to prioritize, what can we lay out and route first. And then the whole PCB is a compromise and there's many, many different things. And there are many different versions of the PCB we could create depending on what we prioritize above something else. That being said, with the layout, we want to first of all do a rough layout, approximately where are the connectors, where's the MCU, and so on. And then we fine-tune our layout and add in smaller components. Also, we might want to do layout section by section. That is, for example, the LDO regulator has C1 and C2 next to it. So maybe we can put those together and then lay those out as a section. So we move C1, U1, and C2 together as a whole rather than individually when we do our layout. So there's many different ways of attempting this, but let's see how I, for example, would do it in just this first iteration. So this particular board I haven't laid out or routed before, so there could be many other ways and equally good ways of doing this. This would just be the first thing, for example, that comes into my mind. So zooming out a bit, we can see the microcontroller in the center here. We still have a grid of 1 mm, and let me just rotate this microcontroller. So if I click on this microcontroller, press R, you can see I can rotate. And this is just personal preference because I've designed a similar board like this. If I rotate it once, that my RF pin is to the right and that my serial wire debug connections are to the right, we'll see why that makes sense in just a second. This reference designator, which is actually on the silkscreen layer, so the front silkscreen layer, I can click and press M, R to rotate, and I can just move that out of the way, for example, or you can hide this layer by on the right hand side clicking the little I symbol, and that hides the silkscreen layer if you would like to do that. What I'd like to then take next, we can see on the left-hand side, we have the USB differential pair and the serial wire debug. So that looks like those connectors should be to the left of our microcontroller. So either in the PCB, we can find those connectors, or on the schematic on the left-hand side, I can click on the tag connect header, which then selects it in the PCB editor, press M to move, zoom out with the mouse wheel, click and drag with the middle mouse wheel, and I can place it, for example, left of the microcontroller. If I rotate the part, we can maybe see already a somewhat optimal location. And to me, that would be, for example, like so. This rotation to me is optimal, well, and more optimal than, for example, 180 degrees, because now the main signals such as data I/O, clock, and trace face exactly where they need to be. So these rat's nests, these air wires, go pretty much straight into those pads. DIO goes straight to the left to right, clock goes left to right, trace goes left to right. Whereas less critical signals, such as serial wired reset or the 3.3 volt and ground, they can be routed anyhow. The length isn't particularly important, especially for this end reset, which needs to go to the bottom. Planning ahead in my head, I could route this out later on, for example, like a little loop like so. This could be an example. But we're doing rough layout right now. Of course, it probably makes sense to move this connector, so pressing M a bit further away, that we have space in case there need to be any decoupling capacitors, which it looks like they need to be for pin 40. But this might be an initial guess. Then, for example, our USB differential pair looks to be above it. So on the schematic again, navigate into the left-hand side, clicking on J1, our USB connector, then in the PCB editor, press M. I can move that, rotate it with R, so that could maybe sit at the top right above. So in this way, we would have a short connection USB-D-D+, that could route into our USB-C connector. That, of course, would be one option. Of course, keep in mind, it depends on board outlines and so on, or we could place it like so. In this way, we have everything on a line, which could make our board maybe narrower in the vertical dimension, and we could still route out our USB differential pair above like so, past the serial wire debug connector into our USB-D-D+ differential pair. So that could be an option as well, and it would also leave more space for the pins at the top, the switch trains power supply LX pins, where we know we need some components at the top here. So again, it depends on preference. what you want to prioritize, and this could be that our initial rough layout isn't the final layout, but it could be a starting point. So it's up to you if you want to go this route, or if maybe you want to go this route. Both in my eyes are fairly okay, but I'll just go with this for now. On this topic, of course, I'm very, very free with how I design this board. In this particular tutorial video, I don't have any mechanical constraints. For example, there's no mechanical engineering team telling me I need mounting holes here and the board outline needs to be a certain shape and I have these constrained dimensions. This, of course, will change your layout considerably. Let's say I'm only allowed to do a small rectangle like so. Then of course I can only place my USB connector here. I wouldn't have space to put it here. So it really depends if you're fitting this to an enclosure, if you're not, if you have any mechanical constraints and so on. Keep this in this video in mind that this layout is very, very free. I have pretty much next to no mechanical constraints. Of course I don't want to make the board arbitrarily large, so I wouldn't want to put my USB connector here or my MCU over here. I want to make it fairly compact because a larger board of course increases cost, and there really isn't a reason to make it excessively large. Same way, we don't want to make this excessively small. We don't want to move these components so close together that, okay, it might still be manufacturable, but we might have to jump to a double layer assembly. So there's always this compromise, and this comes with experience with doing this over and over again, that there are different solutions, but they might all be equivalent solutions or very similar solutions that all work relatively well. Again, keep in mind mechanical constraints can considerably impact the layout and routing of a design. In this case, we are very, very free, so please do keep that in mind. In any case, this might be an initial guess of where these connectors might be. This gives us maybe later on a nice elongated shape, as you saw the PCB in the beginning of the video. The real-life PCB that I had made previously follows this kind of shape as well. And also, placing the USB connector on this side and the tag connect head on this side means on the right side, because we've colored our RF net as yellow, we can simply route out RF to the right side, so far away from the CLY debug and far away from the USB differential pair. Also far away from the switch node nodes, which are these pink nodes over here. So the next critical section, or the next connector we might want to add in, is the RF or the antenna. So for example, our UFL connector, J4, if I click on that and M to move again, this will have to be somewhat to the right side of the MCU. So for example, somewhere here. Now I could place it over here, for example, right next to U2, but keep in mind, we still have the filter, we still have the Pi matching network in between that needs to fit in between U2 and J4. So therefore, already I'll give myself just some space, approximately that I know, okay, something has to fit in between this RF pin and this UFL connector. So something like so as an initial guess. Again, this is rough layout. Now I could immediately place the filter down. So I click on the filter, press M to move. I could place the filter very roughly where it needs to be. And then I could take my matching network and place it next to it and figure out a rough size immediately straight away. That would be one way of doing it, completely fine. Another way is maybe first of all focusing on all other parts, making sure everything fits around, and then we can define maybe a board outline. Again, there are many paths that lead to Rome, so to speak. X2 is another critical component. That's our crystal oscillator for the high-speed external. So I could click on X2. This is this 4-pin package, press M to move. And again, following the rat's nest, you can see the rat's nest are very long and we want to minimize our trace length. So it looks like it has to fit somewhere up over here. And that's why these rat's nests are so useful. We have HEC in and HEC out. So for example, HEC out and HEC in look like they have to loop around. So I can press M, rotate like so, and maybe that's a better placement. Again, we will fine tune the layout later on, but approximately our high-speed external crystal needs to be somewhere close to pins 24, 25, and that's derived, for example, from using the rat's nest. Same thing for the low-speed external. So X1, press M to move, and we can immediately see the rat's nests also lead to these capacitors, the load capacitors, C17 and C18, but if we move X1 closer to U2, you can see these rat's nests jump because we have these multiple connection points. So whatever it's closer to, the rat's nest will jump to. And these happen to be the bottom pins of U2. So U2 seems to be here and the rat's nests are crossing. So the way we can solve that is press R twice to rotate the component by 180 degrees. And it looks like X1 should be somewhere around here. The way it's placed right now is good because now we have symmetry between the center line of pins 2 and 3 and we have symmetrical connections routing out. Again, this will come to with finer tuning of layout later on. But if I move this, for example, very close, then I won't be able to route out maybe pin 4 and pin 1. So even with this rough layout, I still want to give myself some space. Again, always thinking ahead. What's also important is, of course, the switch node. So L1, L2, and so on. So I'll take L1 first, press M to move. Again, following the rat's nest, we can see on the left-hand side it wants to go to U2. On the right-hand side, it wants to go to L2. But U2, pin 33, if we zoom in, we can see pin 33 is that LX pin, which is a switch node. This is a comparatively high current pin. It's switching at a very fast rate, probably fast edge rates as well. Therefore, we want to keep this node short. So I could either place this inductor maybe something like so, but then that blocks maybe other pins, such as these 35, pins 34, and the ground pins. So by taking this component and pressing R to rotate, this allows me some more space maybe to route out the other pins. Again, thinking ahead, not placing parts too close. If I place it too close, I might even be able to route it out, but assembly and testing might be difficult as well. So give yourself reasonable amounts of space. Then L2, this is in a bit of an odd construction because effectively L1 and L2 form, so to speak, a single inductor, but that might sit somewhere like so. And then, of course, we have our output capacitor C14, and these three components form the whole switch node filter. And keep in mind, again, this is a very, very rough placement. I'll show you how to place them much better in just a second. Finally, we have maybe less critical components, such as the LDO or the UART header. For example, if I click on the UART header, M to move, again, following the rat's nests, this is a bit difficult because the rat's nests actually go through the TX-RX resistors. So by placing J2 first, I don't actually know where to go unless I look at the pins, which happen to be 11 and 12. Or alternatively, I could pick up R3 and R4, and that would tell me a bit more just by looking at the rat's nest that we have to go to the bottom right. So many ways of doing it. I could look at the pins or look at the rat's nest. But for example, R3 and R4 should sit somewhere down at the bottom, and therefore our connector might sit somewhere at the bottom as well, just as an example. And so as you're seeing, we're taking these larger blocks, so not always these individual resistors, but with these larger blocks, such as the microcontroller, connectors, more critical main parts of the circuitry, and placing them approximately where we think they need to go, based on rat's nest prioritizing. For example, RF is more sensitive than, for example, the UART connector, and so on. And in this way, we start forming the basics of our layout. Again, for more complicated designs, you will have to compromise even more. This is fairly straightforward, and we don't have, particular mechanical constraints. So the shape of the board or the shape or the placement of components somewhat naturally falls into place, but you'll find with many PCB designs, this is actually the case. From this, we of course need to add in the other components as well before we fine-tune our layout. So for example, X1 still needs these load capacitors C17, C18, or we still have to put in the matching networks and so on. Once we place them into part, we might have to space components out a bit more, and then we fine-tune and fine-tune and fine-tune the layout. Keep in mind, we haven't even popped in the bypass and decoupling capacitors as well. So this is another thing to do. But let's put in the main components first, and then we can add in the bypass decoupling capacitors as well. So for example, D1. We click on D1, this was the ESD protection for the USB. That needs to be in line with J1 and U2. So it looks like we have to move J3 a bit to the right to make sure this fits in. And of course, you want to give it some bit of space as well. You can also see this pink layer, courtyard layer, tells us about the minimum clearance these components should have to each other. And this is part of the footprint itself. So putting in components like so is fine. These are fairly close together. But for example, overlapping courtyards or overlapping pads is a no-go. So something like this might be more suitable. Keep in mind, we're routing in, for example, from J1 into D1, which is fine. But then out of D1, we might have problems getting past these non-plated through holes to get to U2. So we might want to select and drag and move these components out a bit more so that gives us room to breathe. Again, an iterative process, making sure you plan your layout ahead of time while you're doing it, because a good layout will make your routing so much easier. And this will hopefully minimize the numbers of vias you need to use, the transitions between layers, the layer counts, and so on. So it really pays off to do a good job at layout. Then for example, the RF section, we have C15, L3, C16. And this could be, for example, a structure like so. I'll change the grid to maybe one smaller, so that lets me align the components a bit better. For example, something like so. I could place C15 closer to the device, and that might be a good idea because it reduces the trace length of RF traces, which is generally what we want, but it makes routing out pin 20, 22, 23 much harder. Also keep in mind we still have to have decoupling capacitors there in just a second, so maybe this whole structure will be better off just a bit further away. Also, again, this will become with fine tuning. We want to try and maintain straight paths and not these angled paths of our rat's nest. So we want to move these RF components to be in line that we have either vertical or horizontal rat's nest. So we can change the grid that it's somewhat horizontal, for example. For example, if we double click on this pad, we can see the X position, despite U2 being the center, is not quite fitting to any grid we have. So this is always a compromise. But this, at least, we could route pretty much straight out, and then we can move these components in line. For example, so later on, we can just route out into these components, into the filter, and, for example, into our UFL connector. Then, of course, the Silkscreen you can move around just to make things a bit easier to read. For example, something like this. What I'd also highly suggest is Alt-3 to go to the 3D viewer, because oftentimes you can spot mistakes or mechanical errors in the 3D viewer. For example, like so, we can see what our board would look like physically in the real world, so to speak, and I use the 3D viewer a lot of times to do mechanical checks, sanity checks, and so on. So this is maybe what our structures would then look like in real life. And we can see we have plenty of room to the right side to then later route out. But we could, of course, move all these components maybe further in as well. Again, this is an iterative process. We adjust and adjust. You'll probably have noticed that I'm keeping things, for example, the boot 0 switch and the LDO regulators and the LED to right at the end because their position really isn't entirely critical in this design. So we just want a rough placement. I'm placing in all the critical parts first, and then we'll place in, for example, these DC components such as the boot 0 switch and regulator. So for example, the load capacitors C17, C18, we can already take, guided by the rat's nest, they should be somewhere next to this crystal oscillator. So C18, that needs to be then to the left side, for example. And same thing with the placement here. We might be jumping into the fine tuning already. I could place this capacitor, for example, like so, or rotate it at 180 degrees. What might be an option also with these capacitors is to place X1 a bit further down and have these capacitors, for example, in line like so. This means we go straight out from pins 2 and 3 into the capacitors into the crystal. And that might be slightly more optimal than the configuration like so. But then again, for this, it doesn't particularly matter. But here you can see we route into the crystal and then out again of the crystal into the load caps. Whereas this, we have pretty much just one connection, so to speak. Again, this will be fine-tuning when we come to fine-tuning layout and when routing as well. Also going back to the switch mode power supply, we've done our rough placement here, just approximately where it needs to be. But again, if we move the L1 inductor a bit to the left, we have a straight vertical connection later on with routing, and we don't have to do funny angles with our traces. Same thing with the other inductor at the top here. Maybe we can move that a bit closer, that we have a very short connection for the switch nodes, and then the output node of the inductor to the right, we could leave C14 like so, but C14, we later have to route from pad 2 to pad 1 into pad 31 here. So maybe we could move the capacitor more in like so, and we have a shorter connection, or we could rotate this connection that we have closer points between these ground pads. So there's many, many different options available. Maybe something like so would work. Again, Alt-3 to check this in 3D to see how our placement would be. Now, it doesn't look particularly pretty at the moment, but again, iterative process, I can't say it enough. So something like this as a first guess. I've cleaned up the Silkscreen maybe just a tiny bit so we don't have overlapping Silkscreen. Again, you can just click on these texts and just drag them around with your mouse or press M to move on your keyboard. So for now, we've placed the main or critical components somewhat where they need to be. For example, we could, of course, move this crystal oscillator maybe down just a tiny bit, again, minimizing the traces. But what's really important as well is that we also fit in all of these bypass and decoupling capacitors. So for example, for the microcontroller, we have the small decoupling capacitors, so C4 to C9, C11, C12, and so on. And these need to fit in right next to the 3.3 volt pins. So it could, of course, be that we have to move some components we've previously placed. What I'd like to start with is C12, because it's the VDD-RF decoupling, again, one of the more critical decoupling capacitors. For example, VDD-RF is more critical in my eyes than VBAT decoupling. So I'll take C12, and this is a bit deceiving because if we look at C12, we have one pad that's 3.3 volts, so the other pad is pad 2 ground, and we've got so many 3.3 volt pads everywhere. So why not just take this capacitor, place it somewhere next to this 3.3 volt pad, and we're done. Well, the reason we placed it in the schematic on the left-hand side like so is that we distinctly separated these capacitors to know where they are placed. For example, C12, even though it connects just to 3.3 volts and ground, has this wire going into pad 23. So pad or pin 23 is where we want to place this capacitor. So follow what we've done in the schematic. Because we've delivered design intent in the schematic, we want to move that over to the PCB design. Later on, if we might need to debug this device or test it, if you want to find C12 and it suddenly happens to be next to pin 40, well, that's not particularly great. We put it in the schematic there for a reason. So C12 needs to be next to pin 23, and that should be somewhere over here, as you guessed, next to the RF section. So the RF section is here, and placement of decoupling capacitors is also very important. We don't want to place our decoupling capacitor like so, because then we need a long trace into pad 3. Our ground connection is also far away from the IC itself. What's important for decoupling capacitors, because again, they act as high frequency local energy storage, they need to be close to the relevant power and ground pins. So an optimal position might be something like so. That we have symmetry between pad 23 and pad 22. We can simply route out power and ground, and then we can use power traces or planes to connect it to power and ground from a power source. The problem with this connection is that now our RF trace, if we try to route this out, we have to go at a funny angle, maybe around like so, into the RF trace. And again, this is where compromises come in. So we could leave it like so, but keep in mind pad 20 is also a decoupling capacitor, and this happens to be C8. So if I now also take C8, remember C8 because it's the penultimate, and the penultimate pin is pin 20. So if I take C8 and then place it like we did so, okay, great, we've got great decoupling capacitor placement, but what do we do with RF pin? It has to squeeze between these two, and that's not really an option. So what we can do is we either move, for example, this C12 up a bit, and this is maybe already pretty decent because 23 can maybe wiggle its way with a trace to pad 1 here of C12, and pad 20 can go straight to its decoupling capacitor, and pin 21, RF pin, is pretty much unhindered to go to this matching network. So this might already be a good solution. Let's go to 3D Viewer. And also for assembly, again, this is from experience, just judging by eye, this is plenty of space for assembly between, for example, our bypass capacitors and U2. So we could move our bypass capacitors further in, for example, like so, but then you can see we're crossing the courtyard, which might still be okay for assembly, but for assembly testing purposes, we want to stay that these courtyards don't cross. So something like this might be okay. What's also peculiar about our situation is that pins 19, 18, 17, which you can see in the schematic, are actually GPIOs, though, so they could be used for alternate functions. We're not actually routing them out. And this gives us another luxury that we can place, for example, C8 like so. If we had to route out C19, C18, C17, there is no way we could place C8 like so. Instead, we would have to place maybe C8 something like this, maybe further away, that we can route out all of these pins past this decoupling capacitor. So again, it's a compromise. It depends on how many pins you're routing out and so on. But for us, luckily, as we're not routing out many parts, maybe something like this would be okay. I still see a bit of a problem between pins 23 and pin 1 later on when routing this out, that this isn't a particularly pretty connection, so maybe we move it down a bit, but for now let's just keep these capacitors like so. And this procedure we would just continue for all of the power and ground pins of this device. So we can either go from the schematic route, so for example C4 would be for pin 40, because this is our first pin on U2. So C4, M to move, 40 is somewhere here. And again we have that same dilemma. We could place it like so, because we want to keep short wide traces to the relevant power pins, we want to keep our loop areas small. Our loop is effectively from power to power and from ground to ground. And ground happens to be this large thermal pad underneath the IC. Therefore, if we rotate the capacitor like so, yes, okay, we still have pad 1 close to pad 40, which is a short connection, but our ground loop, so to speak, and this is just a visualization, is larger than if we place it like so, for example. However, if we have the capacitor like so, how do we route out 39 and 41? Well, that's going to be rather difficult. So a compromise is that we do have our capacitor like so, but this is still absolutely fine. You could even place the capacitors on the bottom side with vias, and you would still decouple and bypass this chip just fine. Again, it depends on the situation. But for example, like so, it means we can route out 0-wire DIO and 0-wire clock. However, with this placement of the capacitor, we can now see that our tag connect header needs to move because the courtyards are touching. It might be more difficult to route out DIO, clock, and so on. So we just move that maybe just a bit to the left. And that might mean we have to move these two a bit to the left. And hopefully this illustrates how iterative of a process this is. But anyway, let's continue with our decoupling capacitors. So now we have pin 34, which happens to be VDD SMPS. And here, this is maybe a bit of a special case because we have two bypass or decoupling capacitors. One is C10 and one is C11. Now let's compare the sizes of C11 and C10. C10 is considerably larger than C11. Package size and how you attach the package or the footprint via copper to, for example, vias and traces into your components is the prime influence on inductance. So we can already suspect that C11 will have a lower loop inductance when tied to the power and ground pins correctly compared to C10. So we want to place C11 closer to the relevant power and ground pins, and then C10 we can place further away. C10 we could also call, for example, a bulk decoupling capacitor. So pin 34 needs two capacitors, C11 and C10. So let's take C11, the closer one first, and that has to be somewhere close to pin 34, which happens to be up here. Pin 34 is our VDD SMPS, so that's our input to our switching regulator. So the logical way of rotating the switch would be like so that pad 1 is close to this power. Now we do have pad 32 here as a ground, but we'll be using vias and ground planes anyway to hook up our ground, so something like this might be a good first guess. Then we take C10, M to move, and that might be best placed something like so, but that would then mean we have to move our inductors of the switch node, so maybe we can move it a bit further away, something like this as a first guess. If you look at that in a 3D view, so we have C11, which is closest to this power pin, and then C10, which is a larger bypass capacitor further away. So maybe a structure like this, just as an initial guess, and this might change during layout and routing if we can optimize the things a bit more. What you probably will have noticed is that we also have another pad 35, a 313 volt pad next to it. And that happens to be a VDD pin, pad 35, which we need capacitor C7 for. So if we take C7, where do we place that now? Well, this is a bit difficult because we already placed C11 very close and C10 right there. And we have these two pads that need to have their own decoupling capacitors. Well, need is a strong word. We can probably get away with just having one close local decoupling capacitor, such as the 100 nanofarad capacitor here, and we route out short wide traces, both from 35 and 34, that share these decoupling capacitors. So that would be completely fine, and that's what I've also done in the previous design. However, what you could do is either place maybe this other decoupling capacitor like so, and therefore sacrifice a slightly longer trace, or simply move C10 further away and just place these two decoupling capacitors in parallel, and then have this larger bulk decoupling capacitor further away. And in this way, because you've paralleled capacitors, you do actually reduce your inductance if you tie them to ground and power correctly, and then we can have the larger bulk decoupling capacitor further away. So this might be an option, or we can also just simply get rid of one of these capacitors and then just live as we did before, but we share power between 35 and 34 and one decoupling capacitor here. But for the sake of simplicity, and because we have it on the schematic already, let's just keep these capacitors in parallel like so. Again, this isn't too critical, but of course some thought should go into this. So in your own time, I would like you to continue with this, if you're following along, of course, and the remaining decoupling capacitors, we still have quite a few power pins left to place them around the device. I'll do this now, and I'll get back to you once I'm done with this. Now I've placed all of these decoupling capacitors in their approximate positions where they should be, and there are a few compromises, again, that we had to do. If you've done this on your own, I would like to just share how I might have done this. So for example, you already had placed X1, which was our low speed external crystal with its relevant load caps, again in this configuration, or we could place them like so and then move everything down. That is up to you. The difference is not too big. However, we do have this N reset signal that we have to route out on the bottom, pin 7, past this, as well as we have pin 8 that needs to be decoupled. And of course 11 and 12 are our UART, TX and RX signals. The way I did this is so we could either take these three components, move them a bit to the left, and that gives us more space to route out and reset. And then we could have, for example, pin 8 directly down going into our decoupling capacitor placed like so, or move UART, TX and RX, the resistors, a bit further to the right, and then rotate our bypass decoupling capacitor like so, which would optimize the loop a tiny bit, that we have pin 1 and 8 like so, and the ground closer to the central ground pad. Again, this is some sort of airwire visualization. So this might be more optimal than, for example, this placement. And this was also allowing more space to route out pin 7. The placement of the TX-RX resistors isn't too critical. Typically, if you're using, for example, series resistors for termination, you'd want to place at the output. So in this case, this would be pin 11. You want to place your series resistor closer to the output than to the receiver or the input. So for example, RX is an input, we could place, for example, R4 further away. But because you want to maintain symmetry and make things look somewhat visually appealing, maybe a layout like this would be okay. And again, we could maybe move things around. This is just fine tuning. But the components are still in their approximate locations. We have to compromise between placements of these different components. Similarly, for pins 1 and 3, we see we have two power pins quite close to each other. So pin 1, if we go to the schematic, happens to be VBAT, and that isn't a particularly critical power pin. This should be tied to VDD, which is our 3.3 volts in this case, if we're not using, for example, a battery to keep the real-time clock alive and so on if power is disconnected. We're just simply hooking that up to VDD. So comparing pin 1 to pin 48 is, so to speak, an actual VDD pin, which is more critical. Therefore, it also makes sense maybe to put these bypass and decoupling capacitors closer to pin 48 rather than pin 1. And this actually turns out to be quite helpful because we don't really have much space under pin 1 because we have the LSE, the low-speed external crystal there. So therefore, it can make sense just to either put capacitors C6 and C9, which are the decoupling capacitors for pins 48 and 1, like so. And this means we could have a large interconnect between 48, 1 and these two capacitors, or we could also just simply move up these two capacitors that they are in line with pin 48. Either way is pretty much fine. There's no particular difference. However, if we do have them like so, it might make pin 43, our serial wire debug trace, easier to route out past these components compared to if these components are like so. It gives us less space in this kind of diagonal to route past with our trace connection. So let's keep them like this for now. And in that way, we have most of the critical components placed down. And of course, zooming out, middle mouse wheel, we still have a number of components to place here, but these are, so to speak, far less critical than the components we just placed, and we kind of fine-tuned the layout a bit already. Another thing to note is that, for example, this switch node here, there's anything with LX in the net name, these are pretty critical nodes that should be kept short and also far away from, for example, sensitive nodes such as the high-speed external crystal. So we could move the high-speed external crystal maybe in a bit more, but that moves it closer to these inductors. Now, while this probably still is fine, my preference is just to move this high-speed external crystal a tiny bit further away, which yes, does increase the trace length of the HSE in and HSE out later when routing, but it does place it away further from critical parts. I also don't want to place this HSE crystal, for example, like down here, which might be a similar distance, because that's close to the IF traces. And we really don't want that. We want things to be segmented. We want space because that minimizes crosstalk, noise, cross-coupling, and so on. And that's why a good layout leads to good routing, which leads to good performance of the design later on as well. Of course, when we come to routing, we will probably fine-tune the layout even more. But for the critical components, this is somewhat of a good starting point in my eyes. Of course, there's things to clean up, such as Silkscreen, placements, maybe aligning things on grid. But if you go to View, 3D Viewer, or press Alt-3, we can see that this is a fairly compact, somewhat neat layout and routing. Of course, the board shape or the board outline isn't defined yet, and that's why KiCad just extends it to where the components are. But from this, we could maybe already see an approximate board outline might be something like so. What pains me a tiny bit at the moment is this J2 connector, because without this J2 connector, we could have a much slimmer board outline. So maybe we could move it next to J1 or just keep it there because this is just in fact a demo board and this is okay. With that being said, we still have all of these components down here. So we have, for example, the USB-CC, so the communication channel pull downs. We have everything to do with boot 0. We have all of the LED stuff, as well as, of course, the regulator. So these are the components I would like to place next. What's most critical out of all these components? To me, the next thing I would probably want to place is everything to do with the regulator. So that's U1, it's C1, which is the input bypass capacitor, and C2, the output bypass capacitor. We do also have C3, which you probably will have noticed, which is also part of the bypass and decoupling network for the microcontroller. And again, this is what's known as a bulk bypass or bulk decoupling capacitor. It's considerably larger than these smaller capacitors, so 100 nanofarads and so on, and it doesn't have a specific pin it needs to go next to. we've covered all of the pins with these direct connections to C4, C5, C6, all of these 100 nanofarad capacitors, and this larger 4.7 microfarad capacitor, we can take, again, press M, and this needs to be placed somewhere close to the package. So we don't want to place it somewhere from the distance, but we want to place it somewhere close, somewhere where it makes sense, and somewhere where we still have free space. So this could, for example, be over here, but then again, we don't really have any 3.3 volt pins on this side of the package. It could be here, but that means we need to space out our components more. This might be an okay solution, but it just needs to be somewhere close to the package, so maybe somewhere like here is okay. This is close to these power pins, and we could make maybe a polygon pole later on. It needs to be somewhere close to the package, and that's all. So it's fairly loose constraint of where this bypass capacitor needs to be. Okay, with that capacitor placed, let's go back to the LDO. So that was U1. We can take this part, press M again to move. And now as a guess of where this might want to be, of course, next to where our power entry is. And our power entry is the USB connector on the left-hand side. We have the 5 volt pin, so that's pin 1 is our main 5 volt input. And that should be close to the USB connector ESD protection. Ideally, thinking again ahead to the routing, we want to route from our power and ground, or at least from our A4 and A9 pins, plus 5 volts, first of all into the ESD protection, which is pin 5 of D1. If we look at the symbol for D1, we can see there's actually a TVS diode between ground and 5 volts, so an ESD protection part, which can absorb the brunt of ESD energy before it gets passed, so to speak, downstream. So thinking ahead to routing, we want to route A4 and A9 from the USB connector to pad 5 of D1, and only afterwards we want to take the power. And that's kind of what we indicated on the schematic as well. We route out from A4, A9 to our ESD protection D1, and then we go into C1 and into U1, our LDO. So for example, our placement might be something in line with D1, and we want the bypass capacitors next to it. So C1, I'll take over, press M to move. Let's just place it close to U1 first of all, and C2 will move over, which is our output capacitor between 3.3 volts and ground. So if we keep the U1 orientation like so, take C1, R to rotate, we could place it like so, but then you can see the components overlap, and I quite like symmetry. So we could move, of course, U1 over, move the capacitor like so, but then U1 and D1 have an offset, and that I'm not a fan of that. So let's move it back, but we could, of course, rotate U1. So we could rotate it like so, or 180 degrees like so. The preferred option is like so, because my 5 volt pins now face the D1 5 volts, and we can simply move this part up a tiny bit and then place, for example, our input capacitor C1 next to the power and ground pins 1 and 2. Now it's important here that pin 3 is also called 5 volts here. However, pin 3 is not a power carrying trace, it's not a current carrying trace, it's simply the enable signal. But it can be deceiving if you're just looking at the PCB design on its own. Okay, it looks like 1 and 3 are power. Well, that's why we have the schematic open, because pin 3 is actually an enable signal, and we should place our capacitor C1 like so, and not like so. So therefore, again, close powers and close grounds, anytime you're dealing with something like this. On the opposite side, we have our C2, which is close to pin 5. So we could either place it like so, which would be pretty much symmetrical, or if you wish, you could also place it like so. Again, the distance between 1 and 5 is predominantly what counts, because later on we'll see we're going to be using ground planes for routing. Just for the sake of symmetry, I'll probably put it something like so, maybe move these capacitors in a bit more, and clean up the Silkscreen just a tiny bit. For example, like so. Now if I go to View 3D Viewer, or Alt 3, you can see this placement is somewhat okay. We could probably move in the capacitors a tiny bit more, but it isn't great because C2 now means we extend our board outline further than we really need to, given all of the other components. So maybe it would make sense to move this whole stack of components below D1, because we have J2 at the bottom, which extends our board outline anyway. So if we close that, click and drag, M to move, we could probably just move everything below like so. And then of course rotate, because we want 5 volts still facing up. It also makes sense to have, for example, the input capacitor C1 close to the power pins of our USB power source. In this case, it's the USB Type-C connector. We haven't actually added in any filtering on our 5 volt rail, which is typically a very good idea, and typically you would use a pi filter, so a capacitor, series element such as an inductor or ferrite bead, and then a capacitor afterwards. We've taken pretty much our 5 volts straight away and routed that to be our 5 volt net for C1 going into U1. So it often makes sense to at least put provisions in for a pi filter, but we haven't done this in this video for the sake of simplicity. But in any case, we have C1 close to the power pins because this does provide a tiny bit of ESD protection and filtering despite us not having a dedicated filter there. So something like this position is somewhat suitable for this very, very simple design. The other components we have are, for example, R1 and R2. Looking at the schematic, these are the pull downs, the CC1, CC2, so I can select and drag and move those over or press M. And we can, again, by the rat's nest, tell where they need to be. So we have CC1 at the top, CC2 at the bottom, and these aren't particularly critical signals. They are effectively just pull downs, so we could either place them like so, but we want to route out our 5 volts to the right-hand side. So what I typically do with these USB-C connectors, I'm using this type of construct, is place my CC resistors, for example, parallel to the part top and bottom. For example, something like this, and of course you can also rotate depending on how we want to route these out later on. Something like this is fine. These connections aren't critical. Of course, they have to be there, but how we route them isn't entirely relevant in this case. Having the CC resistors in place, we pretty much just have a few of these components left over. So let me move them in just a tiny bit more to make the board a bit smaller. So we have our LED, so that's R5 and D2. I can move those together. We have all of this boot circuitry with the switch and these capacitors and resistors. Then we have this NRST filtering capacitor C13. And again, judging by the rat's nest, we can see where this needs to go. NRST originates at pin 7 of the microcontroller at the bottom. It'll have to route down somewhere like so, over and into J3. So we could place it here, but that interferes with D-D+. Maybe we could place it somewhere here to start with, or next to these capacitors because that's the route through anyway, maybe something like so. There's many different options of doing this, so let's maybe put it somewhere here. Just so we have a group, thinking ahead of routing, we come down, into the capacitor, out of the capacitor, into the NRST. So what's left to do is, of course, the LED with the current limiting resistor and then the boot 0, pull down along with the very simple debouncing circuit and the switch. Now, I'm not particularly happy about this switch. It is rather large in comparison to all of the components, so we could exchange that by going to the schematic, double-clicking on the part, going to footprint, and then clicking that little library button, and we could change to, for example, a smaller footprint, and feel very free to do that, of course. I'm just going to leave it in for the sake of simplicity, but just keep in mind this doesn't look particularly great. In any case, let's just place the diode first, this LED, so take D2, and let's see where this needs to go, and again from the rat's nest we see it's somewhere up here. Now, it could be up here, it doesn't really matter. We could also place it, for example, next to the USB connector, but keep in mind that we'd have to route a long trace or on a different layer to get to that part. So it probably does make sense to keep it somewhere in the vicinity. Depends, of course, again, if you have mechanical constraints, if you have, for example, light pipes or some sort of opening for an LED in your enclosure, you would, of course, want to place your LED sensibly. For us, it's not too critical, so I'm just going to place it kind of, let's say, in parallel, mechanically speaking, somewhere here. I don't want to place it too close to the RF section because remember this pin 16, to drive the LED we set up as a timer and that'll be switching and we want to keep that away from the RF circuitry as well. Along with that we need the current limiting resistor R5, so M to move that, and we'll move it somewhere next to it. Now we could of course place the resistor like so in a 3D viewer. Let's have a look at that, which still is a fair enough distance, but let's say you want to manually assemble this board. We have the space and there's no real need to place them this close to each other, so we could, for example, place them like so, or even further apart. Don't cramp parts like so unless you really, really need to. That's why we space them out a bit. Give them room to breathe, makes it easier to assemble, troubleshoot, test, and so on. Okay, so the last thing we have to do is, of course, our boot switch and our boot pull down. So our boot pull down resistor is R6, this 5.1K resistor. And let's see where that needs to live. So again, the rat's nest will snap to where it needs to be closest to. And it looks like it's this boot 0 pin. So this boot 0 pin, let's think about how we can maybe route that out. We have the LSE in, LSE out, which have to go directly down. So we can't route the boot 0 to the left. So it'll have to come to the right out like so. But we do also have our SWD reset and this bypass capacitor. So it looks like our bypass capacitor might have to go one grid setting to the right so we can get NRST and boot 0 out like so, which means we have to move our resistors a tiny bit. As you can see, this might not be the final solution. It's an iterative process once again. So our boot 0 resistor, it really doesn't matter where this is. Of course, it should be somewhere in the vicinity where it should be. So we could place it, for example, somewhere like here. But keep in mind, we still have to make our ground and power connections. So that's probably not a good idea. What we could maybe do instead, rather than placing that resistor first, is choosing our switch, which maybe should somewhat be in line with our J2 connector. So if we go to 3D view, we can see we have our user interfaces, we have the USB connector, we have J4, which is our F connector, and our switch all probably along the board boundary. Ideally, all of your connectors should pretty much just be on one side of the board. We're violating that quite a bit at the moment, so we have one USB connector on one side, one antenna connector on one side, and this J2 UART connector on one side. So we could, to make this rule a tiny bit better, place, for example, our J2 connector over here, and that means we only have connectors on two sides. Given that this is a demo board, might not matter too much, but in practice, it's best if you can to keep connectors just on one side of the board, but oftentimes and in many products, you simply cannot do this. So I'll leave it up to you of where you want to place, for example, these connectors or whatever interfaces you're using. We could, for example, swap positions that we have our boot switch right next to the microcontroller, and that puts the boot circuitry then in that place as well. And we have the UART connector, for example, like so over here. This would be an option, but then of course you have to route out our UART connections past the switch into this connector. Whereas this option might be a bit more compact, but then again we have connectors on three sides. Let's just for the sake of it go for this option instead. Then we have R6, which is our boot 0 pull down, C19 and R7. So R7 and C19, very simply speaking, form a group. So we can place that again, following the rat's nest, next to our boot 0 switch. And then we take C19 afterwards, which is boot 0, again not placing too close. So we come from the switch into boot switch through the capacitor resistor, and then through, for example, our boot 0 pull down. And then we can route very easily with short traces, and then one long trace going into the boot 0 pin at the bottom of the microcontroller. For example, keep in mind there are pretty much infinite amount of solutions we could do this with. We could move the capacitors and resistors like so, in line, for example, something like this. Either option is pretty much fine. This is a not particularly critical trace, not particularly critical signal. So something like this might be completely fine. And just like that, going to 3D view, we still haven't defined a board outline yet, but this could be a very simple approximation of how you might go about layout, where you fine tune and fine tune. Keep in mind, this might not be the prettiest layout at the moment. We also have quite a lot of messy Silkscreen and so on, but this might be a starting point where we've prioritized electrical connectivity over, for example, mechanical, because we don't have really any mechanical constraints. So you can, of course, take your time. This is done very quickly for the sake of this video. You can rearrange these components, maybe space them out a bit more, and we'll probably have to rearrange some things when we come to the routing part very shortly. What I'd like to do now, however, is first of all define a board outline. You can see in the 3D viewer, KiCad is still telling us that we don't have a board outline, which is very right, and that's something we should define in a second on a separate layer. We might want to move around the Silkscreen or get rid of it completely, and I would like to add mounting holes as well as fiducial markers. So let's start off with the board outline. I've now closed the schematic editor because we've used most of the information in the schematic to do our layout, and then our routing actually becomes quite straightforward because we've hopefully done somewhat of a good job with layout. So the routing should just be connecting up short segments of track or tracks where they need to go. Again, it pays off to do your layout rather well. To do the board outline, first of all, we have to go on the right-hand side and to layers and then select the edge cuts layer. The edge cuts layer is the outline or the board outline layer. Then we can use the tools in the toolbar on the right, for example, draw a line, draw an arc, to draw a board outline. Now again, you probably will have mechanical constraints if you're designing for your own project. In our case, we don't really have anything. So I'm just going to draw an outline that somewhat fits the components we've now placed very roughly. So I can press draw a line on the right-hand side. I would like to increase my grid. So I can click on this and maybe change to a 1mm grid. I would urge you not to use, for example, odd grids such as 0.25, 0.5, but rather stick whole integer numbers. So for example, like so. Now we can see we have the line to already started. I don't want to draw my outline too close to components. This is because your PCBs will be panelized, they'll be broken out, they'll be routed out. So we need to keep space from the board edge. And typically 0.3mm is a minimum, but I would suggest at least 0.5 millimeter. So for example, like here, I would start my board outline just above this Silkscreen, and that gives me ample space because who knows, we might also have to route past these components. Again, this is pretty free in this case because we don't have a mechanical constraint. So I could, for example, draw a line, click next to the connector. This might already be a bit close. Zoom out with the middle mouse wheel. Click again, and again, please keep in mind this is very rough. Click, right click, cancel, escape to cancel the command. And now if I go to view, 3D viewer, here we go. We have a very crudely drawn board outline. And for this board outline, we can either keep or we can adjust it and then move, for example, the components to fit. For example, the USB connector, we might want to move that it overhangs the board outline a bit. Or this connector, this Molex speaker blade, you want to move forward a bit. Or the boot 0 switch, we want to move down a bit. Things like that we can adjust once we have a board outline in place. Now, rectangular board outlines with sharp 90-degree corners are completely fine, and oftentimes it might be an easier or cheaper method to break out from a panel because we can use what's known as V-cuts, so essentially grooves in the PCB that we can then snap. So this outline would be perfectly fine. If you want to maybe improve the aesthetics or if you prefer them, we can also add in rounded corners by drawing an arc on the right-hand side, that tool, and we could draw an arc. So click, maybe this is just a 1mm arc. We can draw a 90-degree arc just as a template. Click and R to rotate. While I'm holding, I can press N to reduce the grid, and you can see my grid has reduced to 0.5mm, N again to 0.25. And for example, I could just place my arc at the corner, and then I can click on the lines I drew previously and just drag them in or out. And now my board outline, let's go to View 3D Viewer. You can see now I have a rounded corner at the top here, and you can of course change the corner radius, and this might be more visually appealing to you, or if you have mechanical constraints, of course you can change the board outline like so. There are of course much more efficient methods of drawing board outlines. You might get a DXF file or step file from your mechanical team, and there's ways of creating the PCB board outline from a template like that. But let me just adjust the board outline a tiny bit just for the sake of this video, and I'll see you in just a second. For example, a board outline something like this. Now I've moved some connectors around a bit, typically USB-C connectors. The plugs that go into these connectors typically have a tiny bit of overhang, so leaving the connector like so or moving it to the left, maybe 1 or 2 slots, is typically fine, so often having just flush with a board outline can be okay. Now there's things that we can clean up towards the end of the video as well. For example, some of this Silkscreen is very close to the board outline, so I'll typically remove that. For example, also these component designators, the Silkscreen is very close to the board outline, so you can either extend the board outline or move the component designators. Oftentimes you also don't need to even place, or in most cases you don't need to place component designators. It often helps of course if they're prototypes, but in most cases a good assembly drawing means you don't need them, plus we have computers and ECAD tools anyway to look these parts up. In any case, feel free to move components around. This is a very, very rough layout. I know it isn't the prettiest, but it's just to get the point across that it's an iterative process and it takes time, and you can make this much neater, of course, if you wanted to. We'll add some finishing touches toward the end of the video, but we're pretty much ready to start with routing now. We're now ready to start with routing of this board, and hopefully with our layout, which is somewhat decent, this will be fairly straightforward. As with layout, with routing, there are many, many different ways of reaching the same goal. How you've done your layout initially will probably guide your routing. There's things we will clean up with the layout along the way, and I'll show you just some best practices for certain sections of the circuits, for example the RF, power and ground, other traces and so on, differential pairs and whatnot. To start off with, same as we did with layout, we want to start with routing also the most critical parts first. So that might be the RF sections, that might be the switch node power supplies, power and ground, decoupling capacitors, crystals and so on, before we move to less critical sections, for example the boot switch, or these CC resistors and so on, and the UARTs. So what I typically start with before doing any traces is I set up my layers, and I place vias. So you could probably route this board out in 2 layers, which is completely fine. We just have routed power and dedicate the bottom layer to ground. But for the sake of ease, and because there are many benefits to using 4-layer boards, we could use uninterrupted ground and sometimes power planes. Our RF traces are narrower. We get better field control because we have close-up ground and signal planes, so we have closer return paths and more and more. There are many, many benefits other than just routing simplicity to using 4-layer boards, and that's what we're using here, and that's what we set up here. Therefore, the top layer is where we placed all of our components on. The 2 inner layers we will dedicate to planes, and the bottom layer we can use for routing. So the inner 2 layers should be uninterrupted, either ground or power planes. Now typical stack-ups you'll see is top is signal, the first inner layer is ground, then the second inner layer is power, for example 3.3 volts in this case, and the bottom layer is signal again. Now our preferred stack-up I use is signal, ground, ground, signal, and there's many reasons for that, and I'll leave some links in the description box below where I've done some videos on explaining that, and this is the stack-up we'll be using. So we're using signal, ground, ground, signal. So the first thing I like to do is draw the ground planes on the inner 2 layers, so inner 1 and inner 2. Routed power for most PCBs, even for some FPGA based or higher speed, higher edge rate digital logic PCBs, can be fine. And in this case of these simple microcontrollers and for RF, pretty much all RF power is routed, so we don't need a dedicated power plane. So let's go to inner copper 1, which is the layer just below the top copper layer, and let's draw a polygon. This will be our ground plane. To do that, on the right hand side, we can see this add filled zone button, or Ctrl-Shift-Z, make sure your grid is suitable, so I have 0.25 millimeters, and we can start drawing an outline. If I left click, I get this copper zone properties, and I can even choose layer 1 and layer 2, so I'll choose layer 1 for example, and then I'll search for a net, I want my ground, and then I can just fill in these properties. For example, electric properties are the clearance to any other features and minimum width. Clearance, I'll change to 0.3 millimeters, and minimum width, I'll change to 0.15. That's our minimum feature width if you remember back to the design rules. Then pad connections, for example to SMD pads or through-hole pads, we will want thermal relieves, for example on through-hole pads to ease manual assembly and soldering. Otherwise you're fighting against these large power planes. So thermal relief, spoke width, we'll just go with 0.25 and a 0.4 millimeter gap. As an example, again this is just from experience. Fill type, we want a solid fill, and we'll leave the rest as blank. Press OK, and then we can start drawing by clicking. We can draw vertices of this polygon. So I can click and move anywhere, click, click, and I don't have to follow this corner. So I could, for example, just draw the rough rectangular outline of my board, like so, middle mouse button, hold and drag to move along the board, and left click to place the polygon outline. And then we finish at our first node, and there we go. Now you can see this kind of hatched, or these lines indicate that we have a polygon pour here. Then either go to Edit, Fill All Zones, or we can use the shortcut B, and that will then pour the polygon. Now you can see if we go to layer 2, which we've currently selected, because it's gray, this is of course ground, which is the net we selected, and this is now a ground layer or ground polygon directly below our top layer, our front copper layer. So if we right click on the inner copper 1, hide all layers but active, we can examine this inner copper layer, which is a ground net. And only where there are holes in the PCB, for example, the drill holes or plated pads or non-plated through holes, we can see we have some clearance which we defined in the polygon editor or the fill editor. And anytime there's a ground pin, for example, the USB shield or this UART connector, we can see we have this thermal relieves, which are these spokes, which we define a width for, and the clearance between the pad. And this will help with solderability. So anytime we now place any more through holes, such as vias, we will get cutouts in our polygon. So if we double click on this copper layer and then enable it on in2, so inner copper layer 2 as well, click OK, press B to re-pour, we can now see on inner copper 1 we have a ground layer or ground plane, and on inner copper 2 we also have a ground plane. And because we've defined our edge cuts layer, so our outline, we also have our 0.3 millimeter clearance to the outline automatically, and that's why we don't have to follow these corners. We can just draw a rough outline shape and KiCad does the rest. So very nice. Now we have 2 inner ground layers. We can actually hide those layers because they're not too critical at the moment. And we'll just look at the front and bottom copper layer as well as the outline layer. And this just makes our view just a tiny bit easier. Before we continue, I would like to add mounting holes and fiducial markers because they'll constrain our routing as well. Now there's ways of doing it, for example in the PCB editor, but the way one does it in KiCad is actually add fiducial markers and mounting holes in the schematic. So if we go back to the schematic, these are actually part of a component. So we can press A to add component. And if we look for mounting, we can see we have different options for mounting hole. So we have a mounting hole without a connection or a mounting hole with connection. For example, we could tie this mounting hole to ground. And depends on what your enclosure is, your electrical requirements, you would choose one or either. I'll just go with mounting hole with connection, so I'll double click on that. I'll add it to some section of the schematic that's kind of out of the way. Click on this, escape to cancel, and we'll immediately select a footprint. So if I double click on this, footprint, and then we look for mounting hole on the left-hand side, and we can see we get different default mounting holes. So we get M2, we get ISO norms, DIN norms, and so on. Typically, you would go, for example, with an M2 or an M3. Again, this depends on the mechanics. So let's just go with an M3 for now. So for the M3 mounting holes, we need M3 pad because we're connecting this to ground. So double click and also select exclude from bill of materials and press OK. And we'll also hide the value by clicking the show checkbox, and that just gets rid of this value. I can move this designator, copy it, Control-C, Control-V, and I would like to add 4 mounting holes and tie them all to ground. So I'll copy a ground symbol and then just use the wire tool as before. And there we go. Now we have 4 mounting holes in the schematic that we can import onto the PCB design. What I also want to add are what's known as fiducial markers, and you probably will have seen them before. Pretty much every PCB should or will have them. It's these high contrast markers, so we have effectively an exposed pad, which is not tied electrically to anything. with some exposed solder mask around the side. And this gives us a nice high contrast marker. And typically you will find many of them on a PCB. And typically there will be 3 global fiducial markers. So we can see here, bottom left, and top right corner. And there are things such as local fiducial markers as well. The reason we need those are because they help automated assembly. For example, for SMD assembly, we can get the tools with cameras or the automatic optical tools to locate these markers, 3 of them as references, and that will help with, for example, rotations and XY placements and so on to calibrate this to your PCB. And this is what we should add ourselves to PCBs or to the panel. Same thing in KiCad, pressing A on the schematic, we type in Fiducial and we can get this Fiducial marker symbol. I'll just place 1 to start with. Typically I call them FM, so Fiducial marker 1, double click, hide the value again, and it will assign a footprint. We can look for Fiducial on the left hand side, and there are many different types, and this depends on how much space you have on the board, but typically what's recommended is a 1mm pad and a 1mm opening, so that would be quite a large Fiducial marker, something like this. If you have to go smaller because of the board size, then that's fair enough. Then you can choose a smaller one as well. We'll just go with this and see if this fits. So I'll just select that. Again, exclude from bill of materials. As an attribute, press OK. Now you'll need these on both sides of the board. So 3 on top, 3 on bottom if you're doing double-sided assembly. Or you just need 3 of them on the side of the board wherever you're doing SMD assembly. Because we're only doing top-sided assembly, all we need are 3 of these markers. What we could do then, just to indicate on the schematic, is on the right-hand side, go to add a rectangle, and we can just draw just a little bounding box for the sake of it around these components. Copy and label and just say these are mounting holes, brackets M3, and these are the fiducial markers, for example. So it could look something like this. We can save the schematic, go back to the PCB as usual. Then in the PCB, we can go to the top, update PCB with changes, or press F8. Click Update PCB, close, and now we have our 4 mounting holes, which is an M3 mounting hole and 3 fiducial markers. We can see already the mounting holes seem rather large, so we might have to go to M2, but that's a quick change as well. So I can select the footprint, press M to move, and we place it where we have free space, in this case on the schematic on the PCB, and it looks like these are too large, so we can change them in the schematic editor. Again, go into the schematic, bulk edit fields at the top, and change the mounting hole pad to an M2, so click the footprint button, change to M2 pad, and we can change to M2 pad with VIA if you want to get all fancy. So let's just go with that, M2 pad VIA, press OK, save, open the PCB, and then import changes again, press F8, update PCB. There we go, we've got slightly smaller mounting holes now. So we can take those mounting holes and they should be aligned sensibly. Of course, again, keep in mind mechanical constraints. You might have specific positions for your enclosure where they need to be. For us, we just want to place them somewhat sensibly. So aligned vertically and horizontally as far as we can and where we have space, for example. So let me just align them. So now I've aligned quite roughly the mounting holes like so. Again, I could increase the board outline and place these mounting holes more in the corner. This is more for demonstration boards anyway, but you'd of course place these mounting holes where they need to be for your enclosure. If you're designing a custom enclosure, I'd recommend placing these mounting holes integer numbers apart, for example 50mm, 75 and so on, and making sure they are not too close to the board outline as they are here. So you want to still keep clearance from these mounting holes to the board outline. Make sure they follow the design rules. I've also gotten rid of the silkscreen markers because they don't need any. So to do that, you can click on a silkscreen element, double click and change that visible checkbox to off. We have our fiducial markers on the right hand side, and they should be placed away as far apart as possible on separate corners of the board. So for example, 1 I might place at the top left, let's say. Again, this is very crude. 1 I might place next to this mounting hole, top right, and 1 next to this mounting hole, bottom right. Just as a very crude example, the actual position doesn't matter too much as long as they are spaced far enough apart. So something like this maybe, for example. Keep in mind, this isn't the prettiest board. We'll try to clean it up a tiny bit. It's mainly about the principles, and because this is just a demo board and we don't have very much time. With that being said, now we have the mounting holes in place, the fiducial markers, and we placed them before we started routing because, as you see, they are through holes, they are pads, so they do take away space, which we need to be aware of. Now we can finally get started with routing, or at least before that, what I typically do, because we have 2 internal ground planes, or anytime you have internal planes or power planes, I need to place my vias first. Vias are effectively through-hole connections. They're plated through holes which allow us to jump layers. So we could start, for example, on a trace on layer 1, which is our front couple layer, route into a via, and that allows us to do a Z-axis transition, and we can route along on the inner 2 layers or on the bottom layer, for example. The reason we want to use vias and place them first is because all of our ground connections, we want to tie to these internal ground planes. So in 1 and in 2, we've defined our internal ground planes, and we somehow need to get from all of these ground pads, and as you can see, there's quite a few of them, to the internal layers. We use internal layers because this provides us a nice low impedance connection to all the grounds in the circuit. The way we maintain that low impedance, or do low impedance connections, is have short, wide traces going to a via which connects to the internal ground planes. Therefore, what I'd like to do is place a via, and to select a via size, we go to the top left, the drop down, and we use one of the predefined sizes we set up earlier. For now, we'll try and stay with 0.7 and 0.3 millimeters because that's a pretty cheap via to produce. And unless you need to go smaller, I would stick with that as a default size, 0.7 millimeter pad and 0.3 millimeter finished diameter drill hole. So I'll select that. On the right hand side, we can see this little via icon. You can press that or press Ctrl-Shift-V on your keyboard, or click on this and you can see a via icon has appeared. Now, any ground pad, we want to add at least one ground via. So we have a ground pad on the left, we have a ground pad per capacitor here, we have various ground pads all over our PCB. But let's take this capacitor as an example, this vertical one here. We have a ground pad. We don't want to place the ground via directly into the center. We don't want to place it a tiny bit into the pad. We want to place it outside of the pad and far enough outside of the pad that we don't get problems with solder wicking during assembly. These vias, if placed too close to the pad and connected with copper, for example traces, can suck copper paste away from the pad into the via barrel, which can lead to real problems. So we don't want to place it too close, but we also don't want to place it too far, for example up here. We want to place a happy medium, and of course this is somewhat of a rule of thumb, but something like this from experience, let's just say looks good to me. So I can left click and place and escape to cancel. You can really see that the ground via is connected, that the via is grounded. And that's because KiCad assumes, because we simply have on internal 1 and an internal 2 ground layers, that we want to connect to ground. If we had a 3.3 volt plane or polygon in the center, then it would ask us which layer do you want to connect to, or what net do you want to connect to. But quite rightly, we want to connect to ground, and that's what we have here. Then we want a short, wide connection between the ground via and the ground pad. Short and wide reduces inductance. So we choose our trace, let's say a wide trace of 0.5 millimeters. On the right hand side, we can either press the root tracks button or press X and start on the pad and route up to the via. And there we go. We have a short, wide connection from our capacitor pad, trace via into the internal planes. In 3D, going to Alt 3, we can see this is what this connection looks like. Keep in mind, we still have to move all the Silkscreen and so on, but this looks like a great connection, let's call it to me. And this is what I want to do for all of these pads. So I can shift click this selection, the structure we just drew, Control C, and click on the center of the pad, select pad, and then paste it on all similar pads. So all of these capacitors will have similar structures. So I can have this one, I can press R to rotate, Control V to paste, and I can paste all of these via structures like so. So I'd like you to do that on your own design, and I'll see you in just a second. There we go. Now I've added this structure we just copied and pasted to all 0402 components. 0402 because this structure won't work, for example, for these larger capacitors. We have to redo the structure with maybe slightly wider traces and so on. So all these 0402 capacitors now have one via, and generally the recommendation, again, is one via per pad. In certain instances, for example, I haven't placed it just yet, or in some instances I've placed it in a certain direction. For example, this structure here, if I just get rid of that, I could place the via like so, but if I place it like so, how are we going to route out the RF trace? If I place it like so, it interferes with the 3.3 volt pads. So I have to place it, for example, like so, which might not be the most optimal case, but it allows me to route out here. Same thing for this trace. If I place it like so, this is still okay because I can route out pad 16, seemingly fairly comfortable. For example, C4, keep in mind I have to route out DIO and clock past this capacitor. So if I select this section and if I would have placed my via like so, I can't really route past here. So that's why I placed my via connection like so. So similarly, what I'd like you to add is one via, and you'll have to do your own structures for other pads close to the pad, not in the pad, and have one via per pad. So I'll do that right now, and I'll see you in just a second. So now I've added pretty much one via per pad in most cases, but I haven't hooked up everything yet. And it's just for the sake of placing vias because we'll have to be able to route around these vias when we draw our traces in just a bit. In certain cases, it can also help to add, for example, parallel vias, so more than one via per pad. For example, I might do that for these larger capacitors, or for example, with a switch mode circuitry, you can add 2 or more grounded vias and then connect these together rather than with traces, with a polygon pore, very similar how we did the filled zones to the internal layers. And parallel vias can help with thermal properties, for example, carrying away heat from hot components. It can reduce the inductance and so forth. But typically 1 via per pad as a minimum. Sometimes, of course, you won't be able to do that and you'll have to share and so on. This is also true for this RF connection or for this UFL connector. I'll place multiple ground vias close to these large ground pads because we want to reduce the inductance, and we'll just draw polygon pores around these pads later on. But the important thing is that we place vias where we think they need to be, so we have them in place for when we have to start routing out. So pre-planning our vias. We don't necessarily have to draw traces yet, but it can help if we have many of the similar structures as we did with these 0402 pads, that we have them in place already. Another place where we need vias is in fact for this QFN package, which is this microcontroller. If we go to 3D Viewer and press S, for example, toggle 3D models, we can see we have underneath the microcontroller package, we have a large exposed copper pad, and this is both for ground electrical connectivity, but also for thermal connectivity. Effectively, you can think of it as somewhat as a heatsink. Now, this is a very small heatsink, so the way we can increase the effectiveness, and because we have to tie electricity to ground anyway, is by placing vias, in this case, within the pad. And this is okay for these thermal pads within certain constraints. Vias directly in a pad are best for thermal effectiveness because they carry the heat away from the component, through the solder, into the pad, into the internal planes, and the internal planes are of course much larger than the pad and can carry away that thermal energy. The problem is with placing vias in pads is that solder paste, once it's applied before we go through the reflow process of assembling this component, is that solder paste can wick or be sucked through these via drill holes. One way of reducing this effect is by using smaller finished hole diameters of smaller finished drills, or by placing the vias in a certain way. So typically, I would recommend not going larger than a 0.3mm finished hole, ideally with a 0.25mm hole, which is still within not being a cost adder typically. But we'll stay with 0.7 and 0.3mm because that's worked fine for me in the past as well. I wouldn't recommend placing them directly in the center if you're going to do this, but rather a number of them around the perimeter, for example like so, and leaving the center somewhat unpopulated with vias, and we can stagger these vias like so. In that way, we can still have a nice big chunk of solder paste in the center, which isn't sucked through. Of course, this is a compromise again, but we have quite a number of paralleled vias around the perimeter, not directly in the center, so we still get somewhat good thermal properties. So this is some pattern, for example, I would recommend. The more vias you have in parallel, of course, the more chances that the solder paste gets sucked through, but you do get better electrical and thermal properties. So again, it's a compromise. But I found this pattern to work quite well for assembly, as I've used quite a lot of QFN components throughout my career. So something like this would be fine to me. What we also have to consider is not just the ground routing, but also the 3.3 volts. If, for example, layer 2 or layer 1, ideally in this case layer 2 would be a 3.3 volt plane, we could do something similar where we have these short wide traces and vias for the 3.3 volt pads. So what we could do is simply copy the structure, again, place it on the 3.3 volt, and then just change the net to 3.3 volt by double clicking, and then could connect to an internal plane. And this would be very easy, and in this case, this would be no problem as well. Although we're not using an internal 3.3 volt plane in this case, it still makes sense to place these vias because we're going to be spending most of the top layer doing our signal routing. So if this is, for example, the USB differential pair, serial wire debug, all of these other connections, we could, for example, dedicate the bottom layer, bottom copper, to be 3.3 volts, or at least the majority of it, because we'll try and stay on the top layer with most of our other signals. So it does make sense to still place these 3.3 volt trace via structures on the pads we see and pre-plan them as well. So let's do that. So for example, something like I've done here, I've added some further 3.3 vias around the capacitors. And for this, where we're having routed power, it's okay to have further spaced ground and power pair vias. So the grounds are here, for example, the 3.3 volt vias are here. And then we route with, for example, the copper fill polygon pore from the vias through the capacitors and then into the pad. So we have the same structure here from the via, large trace, capacitor, then pad, and so on. For example, here, this via was a compromise because I can't really place it somewhere up here because of the RF constraints. So we can route from the via, wide-ish trace into the capacitor pad into our QFN package. And that's why we have all of these 3.3 volt vias here, via, trace, capacitor, pad, that kind of structure. We can then also start adding in other vias where we think we might need them. For example, this 5 volt pad 5 of D1, because of the USB data traces, which will have to route around this, we need to see if we need a via or not for these 5 volts, but we can add vias already where we think we might need them, again via pre-planning. Of course, these vias, these capacitors, everything still might move, but it's an initial guess, and again, it's an iterative process. Once we have that in place, we're pretty much ready to start routing. As we've done with the previous sections as well, we want to start our routing with the most critical traces. And to me, that is the RF section. It's the switch mode power supply at the top, and on the left-hand side, we have the USB differential pair, as well as the serial wire DY connections. And of course our crystals, but those connections looks like they'll be fairly short as well. So this is somewhat of an order we might want to do this in. Then afterwards, we would route out the lower speed signals such as the N reset, or the boot 0 pins, and then finally finish off with power. Again, it depends on the board you're doing, what's more critical, what isn't. You kind of have to prioritize because, again, it's an optimization problem that probably doesn't have a completely optimal solution. In any case, we want to start with the RF traces, and nicely for us, we've marked them as yellow, so they immediately jump out at us. Remember, when we set up the board and design rules, we looked at controlled impedance traces, and we set up a trace, so track width in the top left. That was a controlled impedance trace, and that was about 0.19 millimeters, and that's the trace width we would like to use. Again, we could go, for example, to the board setup, so go to edit predefined sizes, then go to net classes, and we could, for example, set the RF trace width to be 0.19. So if we set that to be 0.19 and press OK, and then select our trace to be used net class width, then either press X or root traces and click on, for example, our first RF trace. This will be a 0.19 millimeter trace as we see in the bottom left under track width. So we can route in like so, route over like so, through this network, into the filter, out of the filter, into the UFL connection. And that is how easily we've routed out our RF section. Because we've done a proper job of layout, our routing is so much easier. We simply have to come horizontal, 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 very, very easily. Make sure you use the correct track width, but given that this distance is so short, you can probably get away with using other track widths as well. But it's a good practice to do so. And this is why we also see why we placed this pi filter, so C15, L3, and C16 like so. I could have, for example, placed my pi filter maybe like so, or maybe scrunched it up a bit more, which would have been fine as well. So then I have to route vertically, and to the right, and I could maybe reduce this length as well. But typically, some structure like this is very easy because we just have to route horizontally in this case. I wouldn't want to do, for example, some routing like this, and keep in mind this is very crude, where I go in here and then I go out here. This is not good because this creates stubs. Something like this, or as we said, we can also have a compactor version of this, is completely fine. We want to stay that these RF tracks don't have to move around much and don't have to route further than they have to. So some structure like this seems very, very okay to me. Keep in mind, we'll add in some final touches where we'll create better transitions between these large pads and these thin traces, but we'll leave that to the end. Then, for example, the crystals, again, the order, as long as we do all these critical parts first, the order isn't entirely important. Again, we can choose a trace that's maybe similar to our controlled impedance trace, so 0.19 millimeters. I'll just select that. X to start routing from the pad and directly in HEC in pad. For the HEC out, I could go from this pad out to the right and up like so, but I typically don't like coming out of these QFN pads at the wide side, so to speak. So typically I would prefer to come out like so, then go up, and I can change routing directions and, for example, into the pad like so. So something like this. But keep in mind, we still have to route the pad 23 to the capacitor, so we might be better off routing the point 24 up vertically. But this could be just a very straightforward example. What we could also do for the HEC in trace, which might be better, so if I delete that segment, is come out of the HEC in pad on the crystal, but don't go too far left, because too far left would means we get close to this switch mode inductor. So we could keep some distance, so stay further right, and only at the end route into the pad. And that might be a better idea than having the trace further to the left. Is it going to make much of a difference? In this scenario, probably not, but it might be a good practice to do. So similarly for the LSE traces at the bottom, again, sensitive trace, we come out of the pad, left, and into the crystal pad. This would be one way of doing it, and then from the LSE in pad, we still have to go into the capacitor. This doesn't look particularly great. So I'd prefer to go into the capacitor first, and then into the LSE pad. Now for the LSE, if you try to read this out yourself, you'll notice that with the design rules we have in place and the trace widths, that routing out the LSE, LSE out, LSE in, LSE out is fine, but then getting the boot 0 pin out is a bit tedious. So what we could do instead is possibly move down the LEC crystal, and then as we had earlier, possibly just rotate these capacitors like so. That way we can route directly into the capacitors, then into the crystal, and we can route the boot 0 past this capacitor as well as the SWD and reset. So let's try that. So that structure might look something like so. Then we would take our trace of 0.19. Again, I'm choosing this because it's similar width to that of the QFN of this pad. And because 0.19 was our controlled impedance 50 ohm trace, and we might as well use the 50 ohm controlled impedance trace also for other signal traces. So again, press X. For the LSE out, we just route straight into the capacitor, straight into the crystal. For the LSE in, we route out a tiny bit and into the pad. And I'd like you also to do the connections like so, that you either come in vertically or horizontally in the pad. If need be, you can also go at a 45-degree angle, but try to avoid structures like so, where you have these sharpish angles, the triangular shapes going into the pad, and always aim to go in horizontally, vertically, horizontally, or at 45 degrees. Then from the capacitor, straight in to the crystal pad like so. And there we go. And this means now with the same trace width, the boot 0 pin, we can pretty much route, for example, and this is just as a demonstration, I can press / to change routing direction past these capacitors, and that should mean we can also get the SWD and reset past. Of course, we'll have to shift some stuff around, but just as an example, this might be a more efficient routing method. Now we have the RF sections, we've got the external crystal sections done. Let's look at this switch mode power supply before we move to the left-hand side of the board. What we want to look at and what we want to prioritize is this LX or anything with LX. And this is to signify this is the switching node, and switching nodes are very sensitive in switch mode power supplies. They should be kept as short as possible and as reasonable, large enough to be able to sustain the current they need to sustain, but no larger. Given that this is such a low power, low current part, the actual trace width for this isn't terribly important. Even a 0.2mm trace can carry quite a considerable amount of current. So let's see what trace width we start off with. If we double click on a pad, for example this LX pad, we can see the pad size width is 0.25mm. So let's use that as an initial trace width. Let's go to edit predefined sizes and add that one in. Press OK. Then we'll select that trace width. Press X to start routing. And we'll route out a tiny section, but as soon as we're somewhat free, let's change the trace width. The way we can do that while we're routing is press W to increase the trace width. We can also change the grid by pressing N. And we can press W again, or we can press Ctrl W to reduce the trace width. So I'll increase it to, for example, 0.5, and there we go. We've come out the pad a tiny bit, and as soon as we can, and as soon as we have clearance, we expand the trace out. Of course, you can make this a bit neater as well, or the full size of the pad, but something like this is somewhat okay. I can also drag this up a tiny bit, again, changing the grid with pressing N, for example, something like so. So we've done a short connection just to get ourselves free from the clearance constraints. Then we've widened out our trace. Wide trace reduces the inductance, and then we have a wide trace going to this switch node, and then we've done our switch nodes. Very short connections, only as wide as they need be, and we can use this technique of starting with a trace as wide as the pad and then branching out or widening out as soon as we can. Then we have the output node of the inductor, this _FB. This is both the feedback node and the output voltage node, and this can be quite large. So for this, we could do a polygon pour that then goes into the pad, for example, or we can just do a trace. Again, the current requirements here aren't particularly large. To do a polygon pour, what we could do is go on the right-hand side, add filled zone. Remember to change the grid to something sensible. So add filled zone, click above the pad, and then we need to select the net, and it's already selected SMPS_feedback. And we can change the clearance, for example, to be 0.2mm, and pad connections to be solid. We don't need thermal reliefs for this reflow. And then we can just start drawing around. I like to keep my corners at 45, like so, and then we can just draw an outline of a polygon pour that might be suitable for this. And that just then goes into the pad, out of the pad, for example, like so. Then we press B to re-pour, and there we go. Now we've got our own dedicated polygon pour for the switch mode power supply feedback, or the output voltage trace, like so. And of course, we can reduce the pad sizes and so on, increase the clearance. So if I double click, increase clearance to 2.25, press B to re-pour, we can see now it's nicely arced in to the SMPS_feedback pin. So this would be one way, for example, hooking up that feedback or that Vout node. And this is somewhat different to a normal switching regulator where you have feedback separate to the output voltage node. But for example, something like this would be okay. We can also see we have the ground pin here, pin 32, which is sandwiched in between SMPS LX and our switch mode power supply feedback. So either we take one of these vias, somehow try to fit that in, which means we'd have to place the components further apart and route around this via, or what people oftentimes do, what's completely fine to do, change our trace width to the size of the pad, press X, and route the pad directly into our exposed pad. And this is what's done also very much in commercial designs and works completely fine. And this means we don't need to have a via here, and we route directly into the exposed ground pad like so. Now we have some traces that are somewhat critical on the left-hand side. For example, we have the USB differential pair, as well as we have all of the serial wire debug I/O. So let's just start off with the debug I/O because this is a bit easier. We'll just use our control impedance trace width, for example, 0.19. Again, we could set that in the net class. For example, going to edit predefined sizes, net classes, changing to selecting SWD and changing the trace width to be 0.19 millimeters and pressing OK. Then trace or track use net class width, press X to start routing. So the easiest trace is this serial wire debug trace, so we'll start with that. We can route out, watch out for that large through hole, and we can go into the pad. Very, very crudely like so. We'll still clean up the pads and the traces at the end, but this would be one way to route this out. The clock, very similar. As soon as we can, get away from the other pads. We don't want to route, for example, like so, very close to the other trace because that increases crosstalk. What we want to do is not go too close to the capacitor, not close to the trace, but break away, give ourselves ample bit of space. We want to route through these two through holes. We can press N to change the grid, route through into the pad, keeping ample space between the trace and the clock, these two lines, and away from the capacitor. Then the data I/O, we need to make sure, hopefully we can fit past these vias, so let's give this a try. Click on the pad again to start routing because we still have the route tool active, and route past these vias, keeping ample space again. We don't want to hug these. We want to make sure we break away as we can. Like so, we go past this through hole again. Always keep ample space. There's no reason to hug or use the minimal space you have. N to change the grid to make sure we can sliver past through here and into the pad. For example, something like this. And again, this is just a rough routing. You can always clean up your routing afterwards and so on. One problem I'm already probably seeing here is trying to route out this differential pair, given that we have this via constraint and this serial wire debug I/O constraint. So we'll have to see how we do that. We can either move this capacitor further to the left, which gives us more space, or we simply route out our D- and D+ traces somewhat asymmetrically to start with, just to break out, and then we can route out properly. So if I try to route out, you can see KiCad is trying, but because of our clearance constraints, we're not going to be able to make this, unfortunately. So again, we have several options. What probably is easiest and preserves aesthetics, let's call it, is to make the serial wire debug clock trace route lower and then move this 3.3 volt via and trace essentially mirrored across this component, so vertically. So let's try that. So for example, I've now flipped this top via and trace, and this means we have more space for the DIO trace to route out, so I can click and drag and move this a tiny bit, just giving myself ample space to make sure that we can route out this D- D+ differential pair. The SWD clock trace here, making sure it has still enough space from the via, I can drag that, and as soon as I can, break away from the via and break away from this other serial wire debug trace. Now, before we start routing out this differential pair now, keep in mind that we did define, if we go to board setup, in the predefined sizes, a differential pair class with a width of 0.22 millimeters, gap at 0.15, and so on. And we do have to assign that to the net class. So we go to net class, USB, you want to change the DP, so differential pair width to 0.22, and the differential pair gap to 0.15. Then press OK. Then we go to route differential pair, or press 6 while we hover over the pads. We can start immediately drawing out this differential pair, and because we quite nicely now moved the vias and the traces away, we can go out, immediately try to come away from that other trace and don't go too close to that top right via. Keeping ample space, we can now route out towards our connector. So I'll just stop the routing here, for example, because we'd like to do this side first. Similar procedure from the ESD protection as well as from the connector. So if we try from the ESD protection, which then goes to our MCU, we could route out past like so, and into our traces, and that's fine. We can clean this trace up a bit, but we really don't actually need that via, I believe, because that via, that we could just route underneath the component, the 5 volts into this pad, and simply have that ground via there. So let's just get rid of this 5 volt via for now. Again, hover over, press 6, and let's start routing our differential pair, routing up, just trying to stay away from these non-plated through holes and meeting our other connection like so. Again, somewhat crude. Again, this is just a first guess, but might be something okay to start with. I can click and drag and kind of route these out maybe just a tiny bit neater, maybe something like this. Again, you can play around with this just to make sure that our pad exits are horizontal, and before they were quite close, kind of hugging this pad 5, so something like this might be a tiny bit better. And of course we can clean up the whole thing just a tiny bit more as well, but just as an initial guess, this route might be okay. Then we have the other side of the ESD protection, which interfaces effectively with the USB Type-C connector. And remember, we have double the amount of pins here. If we go back to the schematic, because this is USB full speed, what we can just do is tie all the D minuses together, all the D pluses together, which do leave tiny stubs, but for these operating bandwidths, it doesn't really matter. So what we could do, again, hover over these pins and try and route out. Now, if we try and do that, you can see KiCad is complaining because, quite rightly so, we have endpoints here and endpoints at the connector. Now, if we try and do that from the ESD protection side, we might have a tiny bit more luck, but it's not looking great either. So what you could do, you could start a differential pair route like so, maybe clean it up a tiny bit, again, just clicking and dragging. This isn't, of course, entirely differential, but it doesn't really matter for very short segments. And then the rest we can just do by routing single-ended. So just going to the route tracks tool or press X and route out this last tiny segment single-endedly. And this kind of gets around this problem. I know it's a bit of a hack, but we want to make our lives a bit easy, especially if it doesn't really matter. What we do have to take care of is that we have the same track width. So here we had 0.22 millimeters. So we have to create a new predefined size, go to edit predefined sizes and add 0.22 as single-ended. Select 0.22 and simply finish the route by pressing X and just doing a manual route out to these traces like so. And then we can just drag it in, make it a tiny bit neater. And keep in mind, yes, this isn't entirely differential, but again, it doesn't matter for these short distances. What we can then do, because we still have to connect up A7 and B6, and this is where these small stubs come in, again, press X or route single-ended. So from D-, we can simply come out the back, like so. And for D+, we can do, for example, something like this. I know this isn't the prettiest, but trust me, it really doesn't matter for this USB full speed. And there we go. Something like this is absolutely fine for these bandwidths. And we've routed out our differential pair, somewhat crudely, of course, but the distances are so short, the bandwidths are comparatively very small, so this works absolutely no problem. You can, of course, fine-tune and fine-tune, fine-tune. This is just to show a rough routing strategy. With that being said, we've routed out most of the critical parts. So we've done the differential pair, we've done the serial wire debug connector, the RF, of course, the crystals, and now we have predominantly low-speed signals left. For example, the boot 0 pin, we have the SWD reset, of course we have our UART as well, the LED and so on, but these in comparison aren't as critical as the signals we've just routed out, and of course we still have power. Then we have to clean up our board, maybe add some polygon pores, and we're pretty much done. So actually the routing, because we've done somewhat a sensible job for layout, is fairly quick, at least for this very, very simple board. So now let's route out the other traces, and this should be fairly quick before we get on to doing the final power delivery, then cleaning up the board, of course. Make sure we go back to example our 0.19mm trace width. This was our controlled impedance 50 ohm trace, and this is what I would suggest. If you have controlled impedance traces on your board anyway, you might as well just stick with the 50 ohm standard, even if it's something as simple as UART, let's say. We have our boot 0, which looks to be a bit cramped, so let's try and route that one out. So hover over boot 0, pin 4, press X, and let's try and route this out. Keep in mind, we still have to route SWD and reset out as well. So we need to keep space between components and pins. There we go. Let's route past this, past the via, and just break away as soon as we can past the via. And we'll just stop this there because we want to see if we can route out SWD and reset. Then SWD and reset, let's route out. Now we could just let KiCad automatically find a path and then just press OK, but I don't really like that pad exit over here. What we can do is just delete that part of the trace, draw a tiny bit up from the bottom, either by pressing X or just on the trace and into the pad like so, and then drag to clean this up just a tiny bit. And again, you can play around with this quite a bit as well, just to maybe improve the aesthetics and so on. But for example, something like so is what we might do. Now that we have the boot 0 and then reset lines out a tiny bit as well, we also have to be concerned about the UART, TX and RX, because before they did go to a connector that was down here, but now we've moved the connector to the left-hand side. Also, the end reset signal needs to go through a filtering capacitor into the serial wire debug tag connect header. So we have 3 traces that kind of have to go down and then left around this area, and we have one boot 0 that needs to go to the switch. So either we could route, for example, the boot 0, which is this trace here, again pressing X or using the route command tool, in like so, But that would mean that either the NRST and the UART lines would have to route underneath the switch through the capacitor and so on, which doesn't really make much sense. So what would be better to do is route out the NRST, UART, TX and RX lines first, and have the boot 0 jumper on a different layer. So for example, the NRST could route out first, so pressing X through into this capacitor, and you can see I've actually rotated this capacitor. So the ground is now facing top, NRST facing bottom. So we simply route through, out to the top, past this USB differential pair, and we'll adjust this in a bit in just a second, past these two through holes like so into the pad. And then we can hold and drag, and I can press Control to increase the grid granularity like so, and make sure the NRST line is far enough away from the USB differential pair. Keep in mind, along short distances, it isn't too critical, especially for these types of signals. We still want to maximize the space between NRST and, for example, the USB differential pair, but also between NRST and these non-plated through holes of the tag connect header. So just as a crude drawing, something like this might be okay. Then, of course, we have UART, TX, and RX, so we can draw those out, again, using a trace of 0.19 millimeters. Let's do TX first, and making sure our pad entries are nice. So vertical, vertical, and again, we can drag, just make these connections a tiny bit nicer. Again, I don't really like coming out like so, but if we were to go down out vertically, then we'd have to move this whole stack down. So for the sake of time, I'm just going to come out horizontally like so into the pad. And that's completely fine. It's just a personal preference thing for these types of signals. So we're going straight into our series resistors. From our series resistors, we go out. We don't want to hug the other traces. We want to give ourselves ample space and towards the connector. So again, we have a mounting hole here, which we need to get past. So we might have to route, for example, something like so. Again, we'll clean this up because this is too close to the mounting hole now. We still have the other trace. We don't want to hug. These aren't forming a differential pair or anything. They are two separate signal lines. Something like so, staying clear of any other features. So something like this might be okay. We might be too close to the boot 0. It's not going to make too much of a difference, but I like to space out my traces sensibly for something like this. If you can, maximize space between your traces. Something like this is probably okay. Now we do have this mounting hole here, which is going to make this a tiny bit annoying. So what we could do to get ourselves more space is move this capacitor via structure to another side of this regulator. So I'll just take that, R to rotate, and for example, like so. We still have our 3.3 volt pads close and our grounds close as well. So this is fine, and this is an option we explored to start with as well. So now that allows me to space out my UART lines a bit better. So I can delete these segments, press X to route out, and now we can quite easily route into the connector. I still don't like this clearance between mounting hole and these traces, so let me just create some more space, delete that segment, go up a bit more, and come down only when I need to, for example like so, and that allows me to delete this segment, X, give myself some space, and when I'm clear again, I can then route past like so. So click, drag, give myself a bit more space, make this a tiny bit more even. Again, you can fine tune this quite a lot. This is still a fairly rough layout, but anytime you can, you have space, give yourself that space. Again, you can fine tune as much as you want, but it's important to always keep clearance, even if they are just DC signals. I like to space everything out. It's just good practice to do so. And again, you can spend quite a lot of time doing this, but something like this might be an okay starting point. You can see, again, an iterative process, we move stuff around to make space. Then, of course, we still have our boot 0 pin in this connection, which we left for last. And remember this, we want to then jumper over by using the bottom layer to get, for example, to boot 0, to this resistor. What might be better is actually to rotate this whole structure, because there's no reason we want to go from this trace all the way to the left. We could make it easy just by going, for example, to the right side. So I can take all of this and simply RR, rotate. So for example, just rearranging components, it could look something like this. Again, it doesn't really matter in this particular example. What does matter is that we use a via to jumper boot 0 on the bottom layer, then we return or come across somewhere over here again with a via and go into the boot 0 and then to the switch as well. I could, of course, also, going from this boot 0 pin, I could, when I press X, of course, route close to the crystal, but that's not what I want to do. Even though it's a pretty much DC signal, this DC signal can be switched, and we want to stay away if we can, and we can in this case, away from sensitive componentry such as this. So I'll route down a bit, press V, which lets me place a via, and immediately it'll jump to layer 4, which is a bottom layer, and I can simply come across, press V again, return on the top layer, and then route into boot 0. There we go. Now we've jumped from the top layer to the bottom layer, routed across, jump into the top, and then we go to the top layer components, for example. Again, there's many different ways of doing this. Doesn't really matter too much for low speed signals, but because we're using two inner ground planes, so in inner 1 and inner 2, on the top layer, so front copper, all of these signals at the top effectively reference the bottom layer, reference layer 2, and the bottom layer, all the signals reference the third layer, so inner 2. So when we're changing from top to bottom layer, we are also changing reference layers. The question is what happens during that Z-axis transition, the via, where's the reference? So what we do, and that's what's called a transfer via, we can press Ctrl-Shift-V, or this button on the right-hand side, and place a via close to our signal via. And this will place a grounded via close to, for example, boot 0, and we place another transfer via close to boot 0 here. And this just ensures we have a continuous return path also during that Z-axis, that vertical transition throughout the board. And this matters much, much more for higher bandwidth signals, but this is just a demonstration. So now we just have to finish up this very short segments of routing. I still need to place a 3.3 volt via here and hook that up. And then we also have the CC pins, which we can route out. So for example, just pressing X and routing those in like so and in like so. And again, this just demonstrates that once you've done a pretty decent job of layout, and even though we did this quite quickly, you can see the routing part is then fairly straightforward. The LED here as well, we need to get past this ground via. So let me just try and get past this. Staying away from that ground via, keeping space and into the LED. This trace doesn't have to be particularly wide. Keep in mind our LED is only carrying, less than 10 milliamps of current, and then we connect the cathode to the current limiting resistor as well. For example, something like this. And there we go. Now we should have hooked up all of the remaining signal connections. Let's just see if there's anything missing. But it looks like we just have 3.3 volt and ground connections and maybe these power 5 volts from the USB connector remaining, and as well to the UART connector. What we also might have seen is that we did select thermal relieves, any connections on our planes, but for mounting holes, we're not really soldering anything to them, so it doesn't make sense to have thermal relieves. So what we can do is click on one of these mounting holes, select footprint, press E to open options, go to clearance overrides and settings, and then at the bottom, connection to copper zones, we'll change this to solid, press OK and press B, and now you can see we have a solid connection to that mounting hole, and we'll repeat that for the other mounting holes as well. So I've changed that setting for all the mounting holes, and here we go. Now we have solid ground connections from the internal planes to these mounting holes. Now what's left for us to do, at least to start with, is hook up all the grounds and powers. And for that, we want to use wide traces, ideally as wide as the pad. This is not just for DC current carrying capabilities, but also to reduce inductance. So thinner traces have high inductance, whereas if we use, for example, 0.5 millimeter trace compared to a 0.15 millimeter trace, then route the trace, this has a low inductance comparatively. So I can route out, for example, from the USB 5 volts. I can route in, for example, directly into my capacitor of my LDO. I know we said we would route to the TVS diode first and then to the capacitor, but for the sake of time, I'll just do it like this. So from the TVS pad, we can just do this T-bar junction, and that's absolutely fine. And also this T-bar junction on the other side, we can also route, for example, to our 5 volt pad on the other side. Keep in mind, this is a USB Type-C connector, so it's 180 degrees flipped. Again, we can either use polygon pores or traces to connect all of these up. So I could do a polygon pore, just as we did, for example, with a switch mode power supply feedback or output voltage node. But for the sake of time, let me just draw wide traces. So ideally traces as wide as the pad. So I can select, for example, 0.6, press X and hover over, and just route in these traces like so. The power and ground we do like so. We can do little polygon pores for example, the ground pins. Pad 3 was also 5 volts, but if you remember back, looking at the LDO, pad 3 is not a current carrying pin, it's just an enable signal. So for that, we can use a narrower trace, let's say 0.19 millimeters. We route out and just in to the wide trace. Something like that is fine for our enable signal. Then for the output node, we could, for example, do a polygon pore. So on the right-hand side, or press Ctrl-Shift-Z, click somewhere, select 3.3 volts, pad connections solid, press OK, and we can draw the polygon pore as usual. And remember, this needs to encompass the vias as well. And even with polygon pores, of course, you want to maintain clearance. So keep in mind, we have a trace directly underneath. So a connection, for example, to start with, we can draw a polygon pore. And then we can, of course, drag the nodes to clean this up a tiny bit. Something like so. Then I can press B. Now we have a polygon pore at the output of the power pin of the LDO, the capacitor, and the vias that are then used to feed the rest of our power distribution network. So effectively, this is the source of our 3.3 volts, which we then have to hook up. So for example, when we have a 3.3 volt via, then we'd use, for example, the bottom layer. So the bottom layer, if I right click and then hide all layers but active, I get this view, which is just the bottom layer. And at the moment, we just have the via pads and other pads and this one boot 0 trace. So that's why it's quite nice with a 4-layer board. I can use a very wide trace, for example, 0.6 millimeters, press X, and this was the output, those two vias of our regulator, and I can just route through, for example, all of these 3.3 volt connections, for example, like so. That's one way of doing it, and that's very easy, very straightforward. We don't have many connections to do. But what we could also do, so if I undo all of that, for example, to the inner layer, what we could also do is simply copy this polygon pore, so Control C, Control V, select it and press E, then we'll change it just to be the bottom copper layer and change that to 3.3 volts, press OK and press B. And now we can see on the bottom layer, we have a 3.3 volt polygon pore and it's automatically connecting to all the 3.3 volt vias and nothing else. So we have clearance between our traces, which is what we want, and that's what we set in the properties, but it connects to the 3.3 volt vias. And the nice thing is, because we've done it like this, we get a tiny bit of capacitance between the bottom copper layer and the ground layer, which is facing the bottom layer. And because those two layers, so inner copper 2 and bottom copper, are so close, we actually get very, very low inductance of the planes. This is a very good thing for power delivery. Keep in mind, it's definitely not needed for this design. Again, we could have routed power. It depends on how many other signal connections you have and so on. We might have used far more of the bottom copper layer. So you might, of course, think this is complete overkill. Granted, it might be, but using 4 layers enabled us to use far thinner traces for the RF sections to hit that 50 ohms impedance, and also for the USB differential pair. In any case, we can also see this in 3D view, so Alt 3. We can see the top layer doesn't currently have a polygon pore, but the bottom layer has this 3.3 volt polygon pore, like so. So we didn't have to do any further routing, we just hooked up our 3.3 volts as before, with just a single plane, which is quite nice and quite handy. Now I do need to add a 3.3 volt via here for this switch, and of course I need to hook that up to the pad, for example like so. So now we have all of our 3.3 volt connections made, but we also have to hook those 3.3 volt connections also to, for example, to the QFN package of our MCU. And for that, we'll use a similar strategy as we did, for example, with the LX node. We start with a trace that's as wide as the pad, and as soon as we can, and as soon as we have space, we widen out. And we'll do that for all of these pads. And for the ground pad here, pin 22, we won't actually connect that to the exposed pad because this is the RF ground, and we'll make that tie to this capacitor, which then goes via wide trace to an internal ground layer with a via. So for that, we'll use a 0.25 millimeter trace, and we'll simply route out, for example, something like so. And for the 3.3 volts, because we don't have particularly much space, let me just hide the internal layers so we can see it a bit better. X to route out, and we just simply route into the pad, and we can drag our traces a bit just to make the entries and exits a bit neater. You can see the trace is not particularly wide, it's just as wide as the pad because we don't have particularly much space to widen out before we hit the capacitor. And this is fine for these very, very short connections. Keep in mind these are fractions of millimeters, or on the order of millimeters. I did have to remove the HSE out trace, and it looks like we do have to route in from the top. Again, it's not my preferred method, but for example, some route like this is probably okay. Now, I'd like you, if you are following along, of course, to do the same principles as we did with the switch mode power supply LX pin for these 3.3 volt pads that are more easily accessible and that we can widen out these traces. And I'll see you in just a second. Now I've added either trace connections or polygon pores, they're also known as power puddles, to these various 3.3 volt connections. So for example, sometimes you have enough space to start out with a small trace, which is wide enough, just as wide as the pad, then widens out into the pad of the capacitor, wide trace into the via, into the power plane we have on this board. Other times you won't have enough space where you just have to have this thin, short trace, and that's fine as long as it's short enough. And sometimes you might have these multiple capacitors and multiple power pins, which you can connect up using these small polygon pores. These are 3.3 volt pores in this case, which encompass the vias, pads of the capacitors, as well as pads of the QFN or of the IC. This is fine for reflow as well. So we've come pretty far already. We've hooked up pretty much everything, but we still have, of course, the ground connections or some of the ground connections missing. So we could either continue by using these wide traces, short wide traces, and hooking up all of these ground connections like so. So we have just a wide trace, let's say 0.5 millimeter trace, press X, and hook up all of these ground connections like so. And that's completely fine and will work perfectly. But one way that might make it easier, also because now we have a bit of a copper imbalance, because on the top layer we have quite a lot of copper that is etched away. So we just have these small thin traces and most of the board at the top is empty. Then we have the first inner layer, a pretty much solid ground plane, the second inner layer, which is also pretty much a completely solid ground plane, and the bottom copper layer, which is a completely solid, pretty much completely solid 3.3 volt plane. So we have the front copper, which is kind of empty, then we have full layer, full layer, full layer. So what we have to do, and this is called copper balance, and this matters the larger the board is, but it's also wasteful to etch away all of this copper. So within reason, and there are of course exceptions when you shouldn't do this, but for a board like this, we could, for example, pour the top layer with copper. However, if we do this, for example, if we take our inner copper layers and also add the front copper layer with ground, let's do that. Press B to re-pour, and let's look at the front copper layer. We can see we have all of these copper islands now poured as well. We have thermal reliefs on the pads, which is something we would want to help with the small components in tombstoning, for example. But we also have copper. These ground poles are very close to these traces, and any copper close to traces will change the impedance profile. So what we would have to do is either increase the spacing or the clearance of the top copper layer to make sure it's far enough away from these RF pads that it doesn't make a difference. And that's typically 3 times the height of the dielectric. So if we go to Edit Board Setup and look at our physical stack-up again, we have a dielectric that's 0.11 millimeters thick between, for example, top and inner first layer. So we want our clearance to be at least about 0.35 millimeters on the top copper layer. Currently, we have about a 0.3 millimeter clearance, which is just about okay. We'd probably want a tiny bit more clearance than that. Another way we could do this is use a keep-out area. So we could draw a keep-out area around the RF sections. So if I, on the right-hand side, or press Ctrl-Shift-K, I could draw a keep-out area just for the copper fills, for example. And then I could draw that around my RF section, for example, like so, press B, and that would get rid of the copper around my RF traces, for example. But what we'll do instead is we'll just change the clearance to be 0.35, and this won't have too large of an effect on the impedance. So now all the pads and traces have 0.35 millimeters clearance, which is just enough to not affect the impedance by too much. But of course, verify that with your PCB manufacturer. With these copper poles now in place, you could of course just get rid of these large traces. It depends on which route you want to go. If you do go the route of just letting the copper pole or the fill on the top layer do all the ground connections for you, you can of course play with the parameters, for example, that the thermal reliefs have a smaller gap and maybe a larger spoke width, for example, and you can try out different parameters that might suit. But keep in mind in copper balances, making sure that the copper on one side of the component is similarly much as on the other side, especially for these small parts. For example, for these spoke widths, then I would also move the vias back a bit, so the copper of the via doesn't interfere with where there should be a thermal relief, so I'd move them back a bit and adjust my vias, for example, like so. What we also have to do, because we have so many ground planes now, we have front copper ground plane, we have inner 1 and inner 2, we also need to add stitching vias. Stitching vias are effectively, in this case, grounded vias that we place at irregular intervals all across the board, and this makes sure the impedance between these individual ground planes and fills and layers is minimized by having many of these parallel vias that we improve our return paths as well. For this, we can either use the 0.7 and 0.3 millimeter vias, or we can use larger 0.9, 0.4 and place them scattered across the board. So if I select vias, I can place them across the board. Set up a grid that's fairly large, maybe 1 millimeter, and place vias all over the board. The spacing of these vias is determined by the maximum frequency content of the signals on your PCB. For us, that'll most likely be this 2.4 gigahertz Bluetooth link, and we can work out the wavelength by knowing that we have the speed of light, so about 3 times 10 to the 8 meters per second. We divide that by the square root of the dielectric constant, and for us that was about 4.29, and our frequency is about 2.4 gigahertz, so 2.4 times 10 to the 9. This wavelength we have to divide by 20, and this is what's typically known as the critical length, and there's many different types of critical length and equations for this, but a safe approximation is about divide by 20, and then I'm just timesing by 10 to the 3 to get millimeters. So a spacing of about 3 millimeters is what we want for our stitching. So 3 millimeters or smaller. We can go to Inspect, Measure Tool, or Ctrl-Shift-M, so we could even space our vias out further, so now we have a 2 millimeter spacing, but this can't hurt. So let's continue that via stitching. So for example, very roughly, some stitching would look like this. If we go to 3D view, again, Alt-3, we can see that we have loads of these copper pores. Sometimes these are these islands, and it's important that these islands effectively don't float. So they're tied down with vias, which are spaced at the intervals we discussed. I haven't done it completely here, but the idea is that you don't get plain resonances and that you don't get effectively these copper areas that resonate by themselves. And the way you can do that is by stitching, and it also improves the inductance and impedance properties between all of these planes and these copper fills we have in this design. Now, of course, this is very quick, very crude, but for the most part, we are now done with the layout and routing. There are things we can clean up. For example, the differential pairs, of course, look maybe a tiny bit funky and so on. We don't need to do any delay tuning or anything. This is USB 4-speed, so we're pretty much fine in that regard. What we need to do is a design rule check and clean this board up a tiny bit. So you see a lot of this Silkscreen is on top of holes or too close or interfering. We might need to want to add teardrops, remove unused via pads, and so on. So there's a few steps now that we need to take, and this is what you usually do at the end of a PCB design. So the first thing you might do before you go over to DRC is just to clean up the design, make sure everything's connected, and the DRC will of course also tell you that. But for example, make sure that Silkscreen doesn't overlap, and if you are going to use Silkscreen designators, that they aren't on top of holes, under components, and so on. What we also can do to simplify the design rules and let the manufacturer deal with this, we did set this up at the beginning. So if we go to Edit Board Setup, go to Solder Mask and change the solder mask expansion and minimum wet width to 0. And then we'll ask the manufacturer to adjust the solder mask openings as they see fit and how it improves the manufacturing and assembly processes. And this is easier. What I actually normally do in, for example, professional designs is I adjust the solder mask openings myself and of course discussing with the manufacturer, but that is quite a lengthy process, so we won't be discussing this in this video. For now, we can move Silkscreen around, make sure it's not too close to the board, things like that. Make sure to always use the 3D viewer because that's quite helpful. You might detect Silkscreen under components, or for example, this U2 here is on top of the hole and so on. Of course, this is manufactural and the manufacturer might edit that themselves, but I like to send a board off that's quite close to how I want it and not have the manufacturer, so to speak, mess around with my board files too much. You want to be in control of your design. But that would be some of the checks you might want to be doing before we move to the design rule check. Another thing is for these RF sections, what we can do, because we have top copper, underneath we have this ground plane, underneath we have yet another ground plane, and underneath we have yet another power plane. So actually these traces at the top will couple predominantly, of course, just to the plane underneath, but it could be that parts couple also to the bottom, to the lower two planes as well. Now, given the dimensions of a 4-layer board, this isn't actually quite to scale. Layers 1 and 2 and layers 3 and 4 are far, far closer to each other than those 2-layer piles are to each other. So therefore you have a very thick core in between layers 2 and 3, so actually you get very, very, very little coupling. But the overall effect, of course, is if you leave those bottom 2 power and ground planes in and don't do a cutout underneath, is that you actually will reduce the impedance because you do get more coupling. So this needs to be taken care of in more critical systems. In designs such as this, yes, you can add in a cutout, but for the sake of time, we won't do this. Another thing we can do for the RF section is add, for example, teardrops. So we talked about that, for example, these RF traces are comparatively very narrow compared to the width of the pad, and we can actually ease that transition. So what we could do is globally add teardrops. So go to Tools, add teardrops, and we can change certain parameters here. So these teardrops effectively adjust the joint, so to speak, from a wide pad to a narrow trace, or if from track to via, track to pad, and so on. So we could do SMD pads only. And if we just press OK, you can see we add in these teardrops. And these teardrops in 3D, we can see here, we get these transitions between wider pads and narrow traces. You can leave those in, but it could lead to more design rule errors. For us, and for these short distances, actually the impedance discontinuity here is pretty much irrelevant, so we will not add teardrops. What I would recommend you do, however, is go to Tools, Remove Unused Pad Shapes. This is because if we just look at the inner copper layer, we can see we have all these ground connections, which are solid connections to these vias, but then we have these 3.3 volt vias, which still have the pad there, which isn't connected to anything. Now we can get rid of those pads and make sure we have less of a ground plane cutout by going to Tools, Remove Unused Pads, and we'll do vias and pads, and remove. We'll keep the outside pads though, and press OK. Now, if we go to Inner 1, again, we can see the pads have been removed, and press B to repour, and we can see now we get smaller cutouts in our polygons due to that. We do, however, see that closely spaced vias do increase our cutouts and we don't get slivers through them. So for example, going back to the top copper layer, what we could do is we move our 3.3 volt vias further apart, press B to re-pour, and now we see on the inner layer, with these vias spaced further apart, we now have this sliver of copper that can flow through these two vias with their pads removed, and I've done that for the other nets as well. You can see on the bottom copper layer, this is where we have our 3.3 watt polygon that's quite cut up, and that's to be expected because we're leaving start and end layer pads of these vias. Also, it doesn't really matter for this layer because this bottom layer isn't a reference layer. The reference layers are inner 1 and inner 2. Now, with all this in place, we've routed our traces, we've done some very basic checks. Of course, there's plenty more checks you can do, and that's a topic for another video. We can run our design rule check, or DRC for short. The design rule check checks the rules we set up at the start. So these design rules, these constraints, we can also change the severity of the design rules if we get errors or warnings or if we ignore them. And we can run the design rule checker by going to the top. These 3 check marks show the design rules checker window, then click run DRC. We'll check and we have 8 errors. We have no unconnected items, that's good, and ignored tests, we have some here as well. But for us, importantly, are the violations. And if we close this window, we can go to these arrows where there are markers where the design rule checker has found something. So we can open that window again. We see we have hole clearance violations, and these seem all to be the same thing of this USB connector. So we have this non-plated through hole, which are these mounting pins or these mounting holes, and that's too close to these copper features. So we've set up a constraint of 0.26 millimeters, but actually sometimes it's less than that, or sometimes it's 0.194. So there's a couple ways of doing that. The first thing is we set up our clearance constraints to be quite conservative, meaning the manufacturer might still be able to produce this, and we just set up quite strict design rules. So we could relax our design rules and then probably get rid of these errors. We can't move the through hole, but we can, for example, change the shape of the pads and still be okay. So for example, I could select one of these pads that has a violation, press E to bring up the options editor, and then simply adjust the pad. Now, this should be really done in the library because this error is going to come up again and again every time you use this part, or again, relax your constraints. So I'll just change the length of the pad from 1.15 to 1 and compensate the exposition for that change, which is half of the change we had. So that'll be 0.505, press OK. And now you can see the end position of the pad is still the same, but I've reduced the distance from that non-plated through hole to the pad. So if I rerun the design rule check, run DRC, you can see we have 1 violation less because we've solved one of them. So now I've done this for all the other pads as well. If I go to show the design rules checker again, run DRC, we now have 0 errors, 0 warnings, because we've now fixed that. Now, of course, this might come across a bit crude, but I've actually done this before on this footprint, and I use this footprint quite a lot in other designs, and exactly this method works very, very well. We go to 3D view, and then if we remove the SMD components, you can see what we've done with these pads is simply shorten their ends a tiny bit, and this is by 0.15 millimeters, so it doesn't make a very large difference, but it does mean we have better clearance to that non-plated through hole. Again, talk to your manufacturer. That's the preferred route to see if it's manufacturable with the default footprint. Otherwise, you can always adapt the footprint. With that being said, we're pretty much now done with the PCB design. We've done the layout and routing, we've hopefully checked the schematic, and now it's time to check the routing as well. So make sure you have adequate spacing between the traces. If you want to add teardrops, you've removed unused pad shapes. You might want to avoid the additional ground and power planes underneath the RF section. You might want to add test points. You will want to add Silkscreen, maybe your logo, and so on. So there's many, many steps still to come after you've completed layout and routing. You might also clean up the Silkscreen, do mechanical checks. There's a lot to do, and that's actually a future video I'm planning as a PCB design checklist that goes through this in detail. For now, I'm just going to add a tiny bit of Silkscreen, and then we'll move over to generating the manufacturing files and seeing how we can order this board. So other than the checks we talked about, and again, that'll be a future video. I think this video will on its own already be very, very long. There are many checks you should do after a PCB design. For now, I'm just going to add some Silkscreen just to make it look maybe a tiny bit nicer. So I can go to the Silkscreen layer on the right-hand side and use the add text items. So just adding a text. I would, for example, put the name of the board. So STM32 demo, PCB, and then I could add, for example, Silkscreen to the board. Now, of course, this needs to fit. I would recommend a character height and width at least 1 millimeter and a thickness of about 0.1, 0.15 millimeters as the absolute smallest. So for example, something like this, maybe as a bare minimum, really you can get creative, but for the sake of time, I just added some basics. So indicating maybe what the connectors are, this is serial wire debug, UART, your logo or your name, what revision, date or date code, your initials, what connectors do, and so on. Don't forget, of course, pin 1 indications, maybe outline indicators, and so on. So you really can get creative, but there are, of course, some essentials. I would definitely put pin 1 and anode cathode markers as a bare minimum. You could, of course, also add, for example, what this LED does, and so on, but this is just a basic, very basic example. With that being said, now that we've done some very, very basic checks, of course, you should check your PCB very, very thoroughly, make sure everything is in order, communicate with your manufacturer, but then we can actually start generating the manufacturing files, and I'll walk you through the ordering process. Going back to the schematic editor, let's start out with a bill of materials. If you remember back, after we finished the schematic, we went to this bulk edit fields button, and then we added in distributor links, manufacturer part numbers, and this information we want to export to bill of materials, excluding these fiducials and mounting holes. The way we can do that is go to Tools, at the top, Generate BOM or bill of materials, and I've copied a generator script, which you can choose on the left-hand side, and added the custom fields, manufacturer part number, and distributor. This I've placed as a custom Python script in the plugins folder, and all I've done, I simply added manufacturer part number, distributor link in the headers, and then also per row taken from the components. Now if I select that script, at the output I'll just append BOM, so bill of materials, and click generate. Then I can click close and navigate to the directory where my project is, and this is where you'll get whatever your project name is, -bom.csv. So for example, we see the footprint, how many we have, the designator, the value, manufacturer part number, and distributor link. And this is one of the components we need if we want to get our board assembled, is this bill of materials, essentially just telling us what components they are, what the manufacturer is, part number, where to source them, and where they are on the PCB, as in their designators and their values. This can then be used by your PCB manufacturer and assembler to source those components and then correlate those with the PCBs. And the way we correlate them with the PCBs is if we go to the PCB editor, export the footprint position files. And this is effectively the XY coordinates of the centers of the components. So for example, relative to a certain origin, where is the microcontroller placed, or where is this capacitor placed? And this is for the automatic assembly machines to automatically place, rotate those components before soldering. Before we export that file, I would like to set my grid origin and my place file origin to the bottom left of the board. So I'll just set the grid origin to bottom left, and then drill place file origin also to the bottom left. This is typically the datum you would select your origin to be at, so bottom left of the board. Then we go to File, Fabrication Outputs, and then Component Placement. Output directory, we can click the little folder button, just select the project folder, or we can generate a separate, for example, assembly folder. Then we can change the format to either ASCII or CSV. Either is fine, we'll just keep it at ASCII for now. Units as millimeters, and because we only have top-side assembly, this right radio button isn't particularly relevant for us, but typically a single file for the board. The rest you can leave the same and click Generate Position File, close, and then we see this position file appear in the project folder. I'll just call this CPL, so Component Placement File. I'll rename this to .txt. Then if we open this file, we can see we have every single component listed, every component on its individual row. We have what value it is, the package, the position and rotation, and what layer it is on. And this information you would then send along with the bill of materials and what we'll see next, the Gerber files, to your manufacturer and assembler. And let me just create a new folder called manufacturing, and I'll move those parts there. So the bill of materials and component placement file for now. And now, of course, these are the assembly files, but we also need the actual fabrication manufacturing files of the PCB. And a very common but rather old standard is Gerber files. So we can go to File, Fabrication Outputs, Gerbers. This is effectively the data per layer. So we have the copper layers, we have the paste layers, silkscreen layers, mask layers, outline, and so on. And that's what we have to select here. So first of all, the output directory, we will select manufacturing. Then we can choose the layers you want to include. So all the copper layers, we want the paste only on the top layer because we don't have any paste or solder paste requirements on the bottom layer. We want the front silkscreen. We don't actually have any silkscreen on the bottom layer, so we can uncheck that. Top layer mask and bottom layer mask, this is the solder mask, and the edge cuts is the outline layer. We can use the drill place file origin for this, and remove the options for plot footprint values and reference designators. And we'll keep the rest as set. Before we click plot, we can also generate drill files on the bottom right. So click on that. We'll keep plated through hole and non-plated through hole in separate files. Drill units will be millimeters, and we'll leave everything else as standard and click Generate Drill File. Click Close, then go to the manufacturing folder. You'll see we have 2 drill files here now. Then we can click Plot, refill the zone fills, close, and in the manufacturing folder, we will now see all these .gbr files, which are the Gerber files. So to check those files, we can go to KiCad, the main window, and click on Gerber Viewer, File, Open Auto-Detected Files, navigate to Manufacturing, and select everything except the bill of materials and the component placement file and click Open. And this is a check I would always do, is use a Gerber viewer just to check that the exports look correct. So on the right side, I can go to Layers, Hide All, and I would go through, for example, the front copper layer. Then, for example, I would check the inner copper layer, then the second inner copper layer, the bottom copper layer. I can check the non-plated through holes, for example, for the USB connector and the serial wire debug header, plated through holes, which are my vias and, for example, my mounting holes, as well as mask layers for bottom, mask layer top, the top paste layers, as well as, for example, the silkscreen layers. And so this is a final check I would do, and oftentimes you can spot maybe small imperfections in your design just by looking at the Gerbers because they give you a different view angle. Now that we've checked the Gerber files, we take those exported files that were placed, for example, in my case, in the manufacturing folder, or wherever you exported your Gerber files to, we need to place them into an archive. Typically zip or RAR is fine, as you're seeing here. This is just an archive that contains all of the exported Gerber files, because we'll need this later when we upload to our PCB manufacturer. Now that we have the bill of materials, the component placement file, or the pick and place file, as well as our Gerber files all zipped up in an archive, this would be the bare minimum one can send to a manufacturer to get an assembled PCB produced. However, it is very much recommended to add more information. In particular, in our case, we might require control impedance or have certain specifications for our PCBs, and we need to deliver those to our manufacturer as well. Of course, you can use online quoting systems and so on and talk directly to your rep, but it's best to include this information along with your design files or your design outputs. The PDFs I'm showing you here are actually not from KiCad, are some very simple designs of what these additional documents might look like. For one, we have an assembly drawing or assembly information, and effectively that's a PDF render typically of the top and bottom sides of your PCB, depending on where components are. And this allows, for example, manual checks. For example, if we're having manual placements and so on, to see where components are, where components need to be placed, the orientations and so on, and can contain additional assembly notes. So, for example, for the STM32WB PCB I had produced, we have component designators, we have pin 1 indications, orientation indications from the top, and also bottom sides of the PCB in the case of the boards I had produced. Now, I originally had designed this board in a different ECAD tool, but you can do similar things also in KiCad. There are a few tutorials that I'll leave online. One option, for example, going back to KiCad, is using the fabrication layers on the right-hand side. If I just select the fabrication layer, that typically has this information, for example, typically taken from the footprint. We can also add in the edge cuts layer, so show that on the right-hand side. If we export this, for example, as a PDF, this might make a very, very basic assembly drawing. We have component designators, we have pin 1 indications, and so on. So a very simple way to export this as a PDF would be to go to the top, File, Plot, then include layers. For example, we can just choose our fabrication, so f.fab, or if you have bottom layers and so on, and plot on all layers. We can select, for example, just the edge cuts layer to make sure the outline is drawn. We want to plot this as a PDF, and the output directory, just for example, our manufacturing directory, click plot. And this might generate a file that isn't particularly pretty, but it's a very, very basic assembly drawing. So we have component designators drawn, we have the outline drawn, as well as pin 1 indicators for the parts that do have that, or for example, anode, cathode markings for diodes. Now, there are definitely better ways of doing this, but this might do as a very basic drawing. Again, depending on the complexity of the design, you might want to add in additional assembly notes, for example, where to pay attention to, sensitive parts, you might want to add bill of materials directly in the PDF, and so on. Other than, for example, an assembly drawing, what I typically will add, and again, this was created in a different program, but you can also just create this in a Gerber layer or just add a text file, and that's what we'll do. So the manufacturing information document, and this is a very, very basic reduced version, will give some basic information about the PCB, for example, what dimensions, thickness, how many layers, what surface finishes, and so on you might want, and, for example, information on the stack up that you might have chosen or are basing your impedance control calculations on. And then you might also indicate impedance control requirements in that document. For example, we need single and at 50 ohms, what type of trace, so microstrip, what the reference layers are, so on, and what your guess of a trace width might be. and you list that for all the impedances you need in your design, for example. Now this in itself is a very, very simplified fabrication drawing. Typical fabrication notes will include far more information. So for example, for a different design of mine, you would indicate, for example, fabrication notes given to certain IPC standards and so on and so forth. And this will actually be the topic of a future video as well, how to create your own very detailed fabrication notes. This will go into stack-ups, showing different layers, what impedance control requirements there are, a drill drawing, for example, what tolerances you need, and could also include the assembly information in one document, and that's what I've done, for example, on this design as well. Now, you don't have to add this to the design for most of these quick-turn PCB fabrication houses, such as PCBWay. So for example, just the bill of materials, component placement files, and Gerbers are enough, but I would typically add an assembly drawing at a bare minimum, as well as some notes on our PCB requirements, for example. Now, this is incredibly crude, but for example, just a simple text document that you then include in your Gerber zip file will do if you need special requirements. For example, we can just say we need impedance control. We have two different types of impedance that we need. We list those. So we need 50 ohms with a certain tolerance, and that's typically plus minus 10%. We want a single-ended and a microstrip, so an external layer trace. We could also add in that we have a ground fill around the sides with a certain spacing, so you can ask the manufacturer to also adjust that, and then that would be called a coplanar microstrip with ground. Our trace is on layer 1 and it's referencing layer 2, and we've assumed a trace width of about 0.19 millimeters according to the calculators. Then we have another controlled impedance requirement, that's 90 ohms plus minus 10%. This time it's differential, again a microstrip, and we can of course also specify a single-ended impedance requirement, as we can play with the individual trace widths of our differential pair, and for this we'll do 50 ohms plus minus 10% single-ended. Again, layer 1 referencing layer 2, this time we have to give a trace width as well as a trace spacing. We can then ask the manufacturer to confirm the trace widths and spacings, and also adjust the stack up as necessary, because we don't have any particular stringent requirements on what materials they use, and so on, as long as they can hit these impedances. So this document, again, this is incredibly crude. We can just add to the zip file. And this is a very, very basic example. Again, you saw the manufacturing assembly files before, and that's what you really should do for professional level designs. But something like this is completely fine. The reason we haven't actually added more information, so for example, the layer counts, solder mask, silkscreen, all these types of information, is because, for example, if you go via PCBWay, you will use the online quoting service and enter this information manually anyway. For the sake of time and simplicity, we'll just enter the information here, but typically this should always be put in your fabrication notes document. So now with these files in place, we have a very crude assembly drawing. We have the bill of materials, component placement, Gerber, and in the Gerber directory, we have the impedance control notes. Made a typo here. This is then what we can submit to PCBWay. So we can go to PCBWay.com, click on PCB Instant Quote, and we can either enter the information ourselves here, or go to Quick Order PCB on the right, click Add Gerber File, and then open up our zip file or upload that of the Gerbers. And now PCBWay's online system will automatically fit in quite a lot of this information. What we do need to fill in is the layer order from top to bottom. So looking at the zip archive, top was F_CU, then in1_CU, in2_CU, and then B_CU, like so. And this is typically something you would have in your fabrication notes anyway. So click on Submit. It's automatically identified the size of our PCBs. We can choose the quantity. Layers, it's automatically identified as 4. We want FR4. The glass transition temperature of our FR4 is fine. Minimum track spacing, 5 mil is 0.127 millimeters, but 0.127 or 5 mil spacing on track size just isn't a cost adder, so we can just leave it at this. The minimum hole size, we had 0.3 millimeters. And now you can play around. You can have different solder mask colors. Green is of course the cheapest, and white silkscreen is of course the cheapest, so we'll go with that. The surface finish can play quite an important role in your design and manufacturability, solderability, and so on. But for us, we can go with something as simple as hot air surface leveling, and for that I typically go with lead-free. Vias are tinted, but we can see the note here for Gerber files. This choice does not affect anything. Finished copper 1 ounce, inner copper 1 ounce. Yes, I'd like to remove the product number. And here, if we open up customized services, we can click impedance control. And this will also give a hint to the manufacturer that this is what we want. And then we can also add in special requests. And then I would, for example, just add a note, please see impedance control text file in Gerber zip archive, just to hint the manufacturer to this. This would be enough to then place an order for just the bare PCBs, but we do want assembly as well. So we can go with assembly service. If we just check that, we can either have PCBWay source the parts, or we can send them the parts, or we can do a mixture of both. The easiest is, of course, that PCBWay handles the sourcing. So this is turnkey, and we'll leave it as that. The board types we want returned as single pieces, and the assembly is just the top side. Then we type in how many boards we want assembled, and let's say we just want 5. We don't have any sensitive parts, and we don't accept any alternatives or substitutes. Other parameters. Now, if you want a more accurate quote before the sales rep checks your bill of materials and so on, you can enter the number of unique parts and so on here, but we can leave this blank for now. Here we can also add in detailed assembly information, but again, I'd recommend creating a proper assembly drawing and referring your manufacturer to that. Then we can press Save to Cart. We can agree to this. We're not doing anything like this. And what we have to do now is we've already uploaded the Gerber zip archive. We have to upload the assembly information. So we can click on Add File in the middle. We want to upload the bill of materials. So click on that. Double click on the bill of materials, the Centroid file, which is our CPL text, and other files. For example, assembly instructions and so on, we would upload here. And they do need a zip file. So going back to manufacturing, I can right click on my PDF and just compress that to a zip, and then upload other files, and we'll upload the assembly drawing as well. Then click Submit Order Now. And just like that, we've submitted our PCB order for the bare PCBs with assembly, and that PCBWay sources all of these components for us based on our bill of materials. So a pretty straightforward process. So after about a day or two, the sales rep will come back to you with an adjusted quote. If you have special requirements for your PCB, that might increase the cost or change the cost. The assembly cost might change if you have very complex parts, or very small or fine pitch parts that need X-raying and so on. And of course, the component cost isn't filled in yet. But once they come back to you with the final quote, you just say, yes, this is okay or not. You will discuss, for example, impedance control, how they might adjust the trace widths, and they can do this for you. Or you can then adjust the trace widths once the manufacturer has talked to you about what the trace width should be for their stack up and using their impedance control calculations. But that's most of what's to this for these rather simple designs, and hopefully this showed you that this is actually quite straightforward. Just to show you what it might look like, what your manufacturer might get back to you with regards to stack up. So this is then the stack up information they sent back to me after I asked for the specific impedances. So this is a 4-layer board, the one I had produced. We can see copper, then we have prepregs of a certain type, a core with copper either side, prepreg and copper again, and this is pretty much the stack up we had as well. And we can see what their recommended line widths are and what actual impedances you might get, of course within a certain tolerance, as well as trace spacing then for the differential pair. So this is then what you would take, and you can then adjust the design yourself or let the manufacturer adjust the traces, and you of course need to tell them which ones they need to adjust. But I'd strongly suggest always speaking to your manufacturer, getting feedback, and of course also doing this before you even attempt the PCB design, that you know what capabilities, what manufacturing capabilities you can design to. And these are then how the boards turned out. I did create my own panel for these because these were rather small, so I had effectively 3 PCBs in one panel. And as we saw earlier, I actually exposed pretty much all of the pins on the STM32 WB55 MCU, and instead of a UFL connector, I used a chip antenna, and I'll demonstrate how to do that in a future video as well. But other than that, it's pretty much the same board we designed. I have of course tested this, and it works very nicely. So there will be a firmware and getting started guide for using the Bluetooth line of microcontrollers from ST in a future video. So make sure to subscribe so you don't miss out on those videos. In any case, I hope this rather lengthy tutorial was helpful for you, that it showed you how to create a schematic from scratch, how to incorporate a microcontroller, add in all of the supporting circuitry, choose peripherals and pinouts, how to do the PCB layout and routing, and also how to use KiCad 7. Hopefully in just a couple of hours you can see how quickly you can design your own boards and how comparatively easy it is if you follow typical rules of thumb, manufacturer guidelines, datasheets and so forth. So thank you very much for watching this video. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest hardware design, DSP and PCB design videos. There are many different videos on my channel going into more detail than we can in this one very basic video. If you'd like to support the channel, please do check out my courses and sign up to those, as I can go into far greater detail on more advanced topics on those. Again, links in the description below. Thank you so much for watching, and I hope to see you in the next video. Bye bye.